Hello. We are excited to present our recent work on accelerating RISC-V instruction set simulation, and the approach tier compilation is rarely used in low-level virtual machine like RISC-V instruction set architecture, but I think this topic is really interesting if you want to achieve higher speed for such purpose. Okay. So, RISC-V itself is a universal instruction set architecture. Besides the wider adoption in Silicon area, it is indeed used by many applications. Take GKVN, for example, is used by cryptography, and by means of RISC-V instruction set, we can have the strong ecosystem for the tooling support. And since RISC-V itself is widely used, so the performance of its instruction set architecture simulation is crucial, especially when we enter the requirement for multi-core simulations. So here, you already see there are similar model for many core or even the complex multi-core systems. So right now is a challenge that we do need a strong instruction set architecture simulator. Otherwise, it's unlikely to simulate and validate in a short time. So that's the reason we start the research. So we already expressed the demanding and the challenge for the RISC-V ecosystem. So at the moment, we just want to accelerate the execution. So our approach is to adapt, to modify and to change the idea behind high-level language virtual machines such as V8, Haspa, and so on. So we adapt idea of tier JIT compilation into the low-level virtual machine, in particular RISC-V instruction set simulation, and then we want to ensure that the simulator itself is always consuming less system resources. Therefore, we can make the simulation more scalable when we want to achieve the multi-core simulation. I think the system consumption is really key aspect during the simulation. Meanwhile, we want to make sure the code base is small and readable, which suitable for the research purpose. I think most of you already familiar with multi-tier JIT compilation. So the idea behind multi-tier just-in-time compilation is we can convert the complex operation into the much smaller ones. So for the first tier, it usually just nail down the scope for instruction dispatch up to operation, or even for the type systems. And for the second tier, it is usually deploy several optimization techniques. So there are some essential optimization techniques applied in the second tier JIT compiler. And for the last tier JIT compiler, we can apply several aggressive optimization techniques. But the question is, if this approach suitable for low-level virtual machines such as RISC-V instruction set architecture simulator. Before answering the question, we just review the existing work. So here you can see hotspot virtual machine, which is dedicated to Java, and we have the V8, which is dedicated to JavaScript, and PyPy, which is built on top of Python. So these virtual machines are very excellent, and we do want to learn the idea behind this virtual machine. But however, these virtual machines are designed for the high-level virtual machine, meaning that is totally different scenario when we want to focus on RISC-V virtual machine. In the other hand, if we go back to the open source implementation for RISC-V instruction set architecture, we can see there are already some notable implementation. So here, Spike. Spike is a famous virtual machine maintained by RISC-V Foundation. So itself is an interpreter, and it was designed for the correctness. So meaning that many developer and many company can contribute RISC-V and its extension based on the Spike. And the Python 4 is very interesting implementation. It is built on top of Python, which is part of PyPy toolchain. So the Python 4 itself can apply several interesting optimization strategies, and then it's possible to achieve a bit higher performance. However, it consumes too much memory, making it almost impossible to be suitable for multi-core systems simulations. And RV8 was an excellent implementation. However, is now unmaintained, meaning that it's not suitable at the moment. VMIL is the most famous implementation as for the system and the instruction set architecture simulator. It's very, very excellent in the performance. However, it lack of the aggressive optimization. Despite the efficiency, Spike itself as an interpreter still making sense to the ecosystem of silicon and the software developer because it's quite small and efficient, meaning that we do not encounter the potential attack from the JIT implementations. So advanced JIT virtual machines such as V8, there are many security attack surface, and Spike itself is good for reference implementations. VMIL is notable for its TCG, which means tiny codegen. TCG itself is portable, meaning that we can use TCG to generate many architecture, including MIPS and some pseudo instructions. However, its limitation, I mean, the limitation of the QMU is it only implements the batch optimization strategy, and it's unlikely for QMU to change its IR because of the comparability, since it is widely adopted by many companies. So the community member want to make sure QMU can be improved, but at the same time, its compatibility must be ensured. So our idea is we want to accelerate the execution of RISC-V instruction set simulation. Meanwhile, we took the approach we called interpreter first strategy, meaning that we focus on the interpreter at the first time, and then we want to make sure interpreter can work as expected, and then we extend its functionality, such as being a profiler for the whole virtual machine. Also, we want to make the aggressive optimization available by means of offloading the optimization to existing compiler framework such as LLVM. And the last tier JIT compilation should be pluggable, meaning that it's possible to replace LLVM with other implementation. In fact, we are doing such tasks. So we try to integrate systems simulation to validate our work. At the moment, our work is capable of booting and running Linux applications. So our work is no longer just a proof concept. I think it is workable, and it is beneficial to the ecosystem as far as I know. There are several key components. The first thing is an interpreter. In fact, it is used not only for the instruction set simulation, but also it is used for the runtime profiler. So, meaning that it has to correct the runtime information and to identify the performance hotspot. Then it will trigger the JIT compilation on demand. And we designed two-tier just-in-time compilation. So for the first tier compiler, as long as T1C is used for to generate codes very fast. So only batch optimization are present in T1C. And for the tier 2 JIT compiler, it's possible to enable aggressive optimization. At the moment, we use LLVM, and later we will try other advanced optimization framework as well. So right now, I will show you the architecture here. Everything starts batch block. So we just design our own IR, which is quite straightforward and simple. So we just convert the RISC-V instruction into the counterparts defined in our IR, and then we try to figure out the performance bottleneck by means of enabling the runtime profiler. So there are two kinds of conditions. One condition is it is not performance hotspot. So if it is not performance hotspot, I mean for the most case, so we just use the pure interpreter. And then if we are able to determine the performance hotspot, well, we split the two conditions. One is the strong hotspot, meaning that is feasible to invoke LLVM to perform aggressive optimization. And for the remaining case, we call it the potential hotspot. So for this case, it is involved more work. So right now, for the potential hotspot, we try to invoke the tier 1 GIT compiler and generate machine code as fast as we could. And later, we can correct the runtime information. Then it could be the feedback for the further optimizations. Let's focus on the interpreter at the first glance. So, as I mentioned earlier, we designed our IR, which is linear. I mean, this is quite straightforward. Itself is built on top linked list. So, from the diagram, you can see there are many nodes, which becomes the chain of IR nodes. And we apply the technique, so-called block chaining, which was introduced by Keynote. So Keynote used block chaining to reduce the overhead of instruction dispatch. And the technique can help branch prediction, and then it's possible to improve the cache locality since we don't have to pay attention to frequent instruction dispatching. So this technique is quite useful, and we just modify modify our interpreter to make use of the block chaining technique. And we try to analyze the existing RISC-V codes, and we found there is an interesting opportunity to optimize the code. So right now we can apply the idea we call it a micro operation fusion, meaning that we can combine several RISC-V instructions which are executed frequently. So we can combine several RISC-V instructions into a single instruction. So like this, we have found several patterns. So we will just provide the smaller counterparts, meaning that we can eliminate the instruction dispatch overhead. And from the preliminary benchmarking, the technique is quite useful. So you can see take Drystone, for example. Its performance could be improved by applying a single idea, I mean, macro operation fusion. And we apply the common optimization strategies such as constant propagation and constant folding. So apply such optimization strategy, the interpreter could be a bit faster since we can, again, we can eliminate the overhead of the instruction dispatch and get the deterministic execution as well. And as I mentioned earlier, we concentrate on the system resources usage. So it's necessary to ensure our implementation could be function not only for the faster execution, but also to be resources efficient. So we try to integrate some notable memory allocation strategy. So right now, we can use LFU, which is quite straightforward and is quite useful. So we can make the memory consumption as low as possible. Sorry. So we will just pick out some micro benchmark to validate the efficiency. And you can see comparing to the baseline, the strategy is quite positive and quite useful from benchmark perspective. And compared to the spike, our implementation of the interpreter could be much faster. And the next stage is we want to introduce the aggressive strategy to isolate the GIT compilation. So, please.
Maybe 5 more minutes.
Okay.
Okay, here is our design of our GIT compiler. First, we want this compiler translates the IR into the host binary to improve the efficiency. But we want to only compile the hotspot because the overhead of the GIT compilation is heavy. And the benefit from the GIT compilation might be cancelled by this overhead. Our first GIT compiler is the simple one and only does do some optimization, but important one. And if the other one hotspot is detected, we invoke the tier 2 compiler to compile the hotspot. But how do we categorize the hotspot to appropriate GIT compilation? We use the runtime profiler. The runtime profiler divide the hotspot into 2 types, the potential one and the strong one. The potential one is the block which execution count exceeds the threshold we set, or is a part of a loop. The strong one is the potential hotspot. The execution count of the potential hotspot exceeds the threshold again, and it becomes a strong hotspot. This is the workflow of our runtime profiler. If the hotspot is detected, it go to the middle path and generate the target machine code. And the target machine code is invoked. The execution count of the target machine code is exceed to the threshold, and it becomes the strong one and go to the bottom path. And I have mentioned in this page, the second one is the detection of the part of the loop. And how do we detect the loop? We have two methods to we have evaluated 2 methods to detect this loop. The first one is based on the backward jump. If the backward jump detect, we directly offload the execution to the JIT compiler, and this may sometimes break down the internet loop. So we decide not to use this method. And the second one is trace the interpreter execution path. We initialize the set and insert the basic block into the set. If we found the basic block is already in the set, a loop we found. So the second one is better for the loop detection. And the right side is the proposed loop detection. And left side is the first method, and it breaks down the two interloop to the small piece, and we don't want this appearance. Okay. Skip. The implementation of our tier 1 compiler. First, we prepare a code cache. We need to create the executable memory page by the mmap system call, and provide a function product and an app log to reverse the host register value. And the LFU cache replacement is used in our implementation if the code cache is full. The execution flow is shown below. First, we enter the product and jump into the translated block. If there is any change block, it keeps going to the change block, and finally it comes back to the app log and return the control flow to the next to the interpreter of the next block of the JIT compilation. Okay. We introduce another a technique to do the branch prediction to solve the indirect jump problem in a dynamic binary translation. In many dynamic binary translation, the indirect jump we cannot the target address of the indirect jump is determined by the register value in the runtime. So we cannot do the block training before the program is actually executed. So to address this problem, we record the history of the target address when the interpreter is executed, and then once the JIT compiler is executed, is invoked. The most frequent jump target is to we generate a branch instruction for the most frequently jump target.
So wrapping up the conclusion.
Okay.
Okay. The tier 2 compiler we use the LLVM framework.
So I just to summarize the proposed numbers for you. So right now, not this one. So right now, if you compare QMIL and our work, it's possible to assure the feasibility of TLJIT compilation. However, the number was not so evident as we expect earlier. So it is because we still have to nail down some potential performance improvement, such as more indirect jump improvements, as we mentioned earlier. And still, if you compare the work with the native execution, the result was promising. And however, some terms like 14-point emulation and string sort, they were not as good as we expect. So we need more we need more work there. So I think it's an interesting strategy to introduce multi-tier GIT compilation into the system-level simulation, and I think it's doable. However, we figure out some potential improvement strategy, and right now we want to show you the results. And at the moment, it's capable of booting Linux and running complex user program at the moment. Thank you.
Please, let's have some questions. Please, questions. Okay, please.
Thanks for the great talk. So if I understand right, you were using like a place git like upload where you trigger this compilation depending on the hotness of the basic code ideas, and I was just wondering whether you consider using more like a method-based git upload where you trigger this compilation depending on the hotness of the. Can you hear me? Okay.
I think you can just speak. It's not such a big room.
Yeah, but yeah, this is recorded. Sorry. Should I
Yeah.
repeat the question? So if I understand right, if I understand right, I think you're using the trace like JIT where you trigger the compilation depending on the hotness of the basic probe. I was just wondering whether you consider using the more like a method-based JIT.
Okay, so our major idea is we want to speed up the execution of risk-like instruction set simulation, in particular for the multi-core system, meaning that it's impossible to isolate every processor core. We must highlight the performance hotspot, and then we want to offload the aggressive optimization. So our consideration is can we just nail down the system resources utilization at the first moment, and we apply some idea to profile the system not only for the virtual machine aspects, meaning that we do not only the loop detection, but also how can we balance the computing in the multi-core system simulation. So I think there is a room for identify the potential hotspot and try to make it practical for such topic. Thank you.
So especially with LLVM, how do you handle traps and faults like invalid memory accesses.
Okay. The question is about the fault and MNU handling, right?
Sorry?
Your question is about the trap
Yes.
and the fault handling.
Yes.
Okay. For system simulation, that's necessary. And in the paper of VMIL, we lack of such discussion. But it is quite challenging that you have to convert the memory operation since the memory model is different, and including the barrier, memory order, TSC, and so on. So we have to predict the behavior of the running system. So we implement yet another system profiler for Linux system by insert the Linux kernel. So it's some kind like a perf variant to correct this runtime information. And if we can utilize the runtime information, we can then to predict the memory operation and try to replace the operation with the shortcut one. Okay.
Thank you.
We should move on, I think, to the next topic. Thank you. Let's thank the speaker.
Okay, so the next talk will continue the theme of just-in-time compiler, and we're talking about how to reuse compiled code in dynamic language virtual machines. And the speaker will be, I believe, Andrei Pessimuth, and he's from Oracle Labs, and this is joint work with David Leopold-Zelder at Oracle Labs as well, and Petr Tum at Charles University.
Thank you. Hi everyone. So this talk is about reusing. Okay. So wait. Great. So this talk is about reusing compiled code in the context of a modern dynamic compiler. The motivation for this work is VM warmup. When an application starts, its execution speed is usually slower at the beginning, and early in its lifetime, the VM collects execution profiles and compiles the hottest methods. And once compiled code for the most performance-sensitive methods is available, the application usually speeds up. So we call this the warm-up phase, and it's a problem because it is wasteful, it wastes hardware capacity, and it makes the application slower to respond. So in the Java ecosystem, there is a lot of ongoing work to improve warm-up, and in our work, we focus on improving VM warm-up by reusing compilation results from previous runs of the same application on the same VM version. So where our work should ultimately lead to in the future is we want to achieve a setup like this. So we want to build a remote JIT compilation server that can compile code on behalf of remote client VMs, and then it returns the compiled machine code to these clients. The benefit of this is that the compilation server can cache the compiled code, or more generally some compilation results, reuse them for future clients, and these compilations from the cache, they should be faster than compiling from scratch, which reduces the compilation latency, and it should improve the warm-up situation. Now, the challenge with a setup like this is that the compiled machine code is usually not easily reusable. So the problem is that the dynamic compiler specializes the machine code to the state of the running VM instance. So this is often what we want because it usually improves performance, but it also hinders the reusability of that code in another VM instance. So to understand this problem, consider the code on the slide. So we have some method do work that performs some logging based on the value of a static final field. And then it performs the actual work. So how would a performant dynamic compiler optimize this? So of course the optimizations, they happen at the IR level, but for the purpose of the presentation, I showed them as source code. So first, the log level field is declared static final. So in Java, once it has a non-null value, the compiler can load that field value during compilation and fold the load. So suppose that the value of the field is the string none, so it can replace the field load with the actual constant. And now in the code, we can clearly see that the branch condition evaluates to false. So the compiler can remove all the logging code. And suppose now that we store this in the compilation cache. And the problem with this is if another client comes in the future, then it tries to reuse this compiled code. However, the value of the log level field was computed with a static initializer, and there's no guarantee that the next time we invoke that application that the computed value is the same. So if the value of the log level field changes in the future, in another VM instance and application run, then it would be incorrect to reuse this machine code. It would cause some incorrect behavior. So this is the problem. In general, compiled code is not reusable because the compiler specializes it to running VM instance, as I already said. And these are the more specific categories. So the first one is about the non-determinism of the runtime environment itself, and the compiler can somehow specialize to this non-determinism. So what I mean by this, for example, in the hotspot JVM, the compiled code can directly reference VM objects, so the addresses of these objects are embedded inside the compiled code. The problem is that the runtime allocates these objects at different addresses every time the VM is invoked. So reusing that code is usually not correct. Similarly, in the hotspot JVM, the vtable layout may change between runs. So this is another source of non-determinism that the compiler specializes to. The second point is about non-determinism in application code itself. So this is similar to the example we have already seen with the static final fields, but generally there is a problem with final fields, and even very innocent looking application code can suffer from this problem. So suppose that we have an app that stores the current time in a static final field. Now all the code that reads the value of that field, the compiled code will have the current time embedded in itself. So the next time you invoke that application, the time will change, so it would be incorrect to reuse the code from the past runs. Now the third point is about optimizations based on the state of the VM. So as an example, classes in Java have initializers, and when a class is first referenced, the runtime has to invoke that initializer. But there is an optimization in the compiler. If a class is already initialized during compilation, the compiler doesn't need to emit any initialization status checks, which is great for that VM instance. But the next time we rerun the same application and want to reuse that code, then that class may not already be initialized, which would lead to wrong behavior. Lastly, the fourth point is about object references in compiled code. So what I mean by this, the compiled code may reference application objects living on the heap directly, so it may contain their addresses. So when we want to reuse this code, we somehow need to be able to relocate these references so that they point to the heap of the target VM. But this is difficult to do, because how do we find the right objects? Well, objects in Java have identities, so this is not easy at all. I will not go any deeper than this. If you're interested, the paper contains much more details, so I invite you to read the paper. Now, the idea, what do we want to do about this, is we want to reuse the IR instead of the machine code, because the IR is easier to patch and it's also easier to transform, as we'll see. And to make the IR reusable, we will basically defer optimization to a later stage. So to understand this, first consider this simplified view of a compilation pipeline. So we usually start compiling the bytecode, we parse it into an intermediate representation, the compiler applies multiple optimization passes, and finally it emits the machine code. So this is just an illustrative view. Usually there are many more optimization passes. And now we can view it like this. So basically, the individual optimization passes, they apply many transformations, some of which make the IR more specialized to that particular running VM instance, which is often great because it improves performance, but it makes the code non-reusable. So at the beginning, it could be something like folding the read of a static final field. Later in the compilation pipeline, if the IR references some VM objects with a relative address, then this optimization could be something like choosing a specific instruction sequence. So it could maybe select a shorter instruction sequence if that relative address is small enough. So this is a very optimization that is very specific to that particular VM instance. And this is what we actually want to do. So after some specific optimization pass, we cache the IR for later reuse. So we call this the point of reuse. After the point of reuse, basically any VM-specific transformations are allowed. And before the point of reuse, we need to make the IR reusable. So we do one compilation like this where we cache the IR, and the next time we want to compile the same method for another VM instance, we start only from the point of reuse. And we basically apply the rest of the compilation pipeline. And starting from the point of reuse should be much faster than compiling from scratch. And how do we keep the IR usable? Well, the idea is, the high-level idea is that we should move the transformations that specialize the IR to the running VM instance after the point of reuse. So we should not do them before the point of reuse, but hopefully we would be able to perform them after this point of reuse where we're compiling for a specific single VM instance. And we do this by before the point of reuse, we restrict the compiler's access to some VM state, and after the point of reuse, we run an optimization pass that can do many of these transformations. There is the question of where specifically should we cache the IR, where should we place the point of reuse? Well, this depends very much on the concrete compiler implementation, but generally speaking, if we do that at the beginning, then it might be easy to reuse that IR, but we do not save a lot of work because we have to repeat almost the whole compilation pipeline when we want to reuse it. If we save it at the end, then the IR may already be too VM specific and impossible to patch. So to sum up this idea of IR caching and deferred optimization, compiling from the cached IR at the point of reuse should be much quicker than compiling from scratch, which should lower the compilation latency, which should in turn improve warmup. And with deferred optimization, we can cache IR that is less specialized to the running VM instance, but we can still benefit from VM-specific optimizations by applying them after the point of reuse. And the advantage of deferred optimization is also that basically the IR cannot reference arbitrary VM objects, arbitrary application objects living on the heap. It can only reference constant pool objects, so it is much easier to relocate these references. The potential problem with this approach is that by making the reusable IR more general, we also make it bigger, which influences all the subsequent optimization passes. So some optimization opportunities like inlining could be completely lost. And to be able to reuse this IR, we still need to be able to verify the equivalence of class data. So what I mean, the class data that was used to compile the reusable AR should match the class data loaded in the target VM where we want to reuse it. And we would also need to be able to verify all the assumptions made by the compiler during the original compilation. Now for the experiment, we want to find out what is the impact of deferred optimization. So basically, IR caching, implementing IR caching in a production compiler, that's a lot of engineering effort. So instead, we want to just test the feasibility of this idea. And the key question is whether deferred optimization, whether this, what's the quality of that code. So we implemented just deferred optimization for the GraalVM compiler and ran it on the Renaissance benchmark suite. And the implementation works like this. Basically, before the point of reuse, we disable field folding, and all the IR nodes that represent object constants living on the heap, we wrap them in a new kind of IR node that we created for this purpose. Basically, these nodes then become opaque to the compiler, so the compiler cannot specialize to the heap contents during this compilation before the point of reuse. And after the point of reuse, we basically re-enable field folding, unwrap all these IR nodes so that the compiler can start specializing to that particular VM instance. And the results are the following. So this chart shows the slowdown ratios of the GraalVM compiler with deferred optimization compared to the unmodified GraalVM baseline. So starting from the left, the workload Scala STM bench, there's no slowdown. For many workloads, the slowdown is small, and we have one outlier, Ghost Mix, where the slowdown is almost 6x. Basically, deferred optimization can reduce peak performance, but supposing that we can compile from the cache much faster than we could compile from scratch, then this could actually lead to some warmup curve improvements in some of these workloads. This is because the code compiled by the GraalVM compiler that runs much faster, of an order of magnitude faster than the code compiled by the lower tier compiler. So if we could manage to switch to this code much sooner by reducing the compilation latency a lot, then this could actually improve warmup. So Ghost Mix is a clear outlier, so what's going on in there? It turns out that deferred optimization doesn't work with a particular code pattern, and this is about method handles. So method handles in Java, they are a low-level mechanism to indirectly invoke methods. And it is designed in a way that when the method handle is a constant and represents a concrete target method, then the compiler can link it with that target method and inline the target method. The problem is that this doesn't work with deferred optimization. So why is that? The problem is that for this code example, at the beginning, we cannot fold the load of the handle field because we disabled field folding. So the handle is not a constant. And then in the inlining phase, well, the receiver of the call is not a constant, so the compiler cannot find the target method, and it cannot inline it. So it doesn't inline it. After the point of reuse, we re-enable field folding. Now the compiler actually folds the load of the handle field, but it is too late for inlining, so it's not inlined, and this is the cause of that huge slowdown in Ghost Mix. Could we fix it? There is an alternative idea that could potentially lead to better peak performance. But there is a trade-off between the complexity of the implementation and well, performance. The alternative idea is that we would defer only the transformations that are likely to be invalid in future VM instances. So this approach would be more optimistic. But for this to work, we would need to be able to select which transformation should actually be deferred. And we would also need to be able to verify that for all the transformations that were actually performed, so not deferred, whether they are valid in a particular VM instance. And also, now the compiled code could actually reference arbitrary heap objects, so we would need to be able to patch these. So as I said, this could lead to better performance, but there is a trade-off between complexity of the implementation and performance. To conclude, the compiled machine code is usually not reusable because the compiler specializes it to the running VM instance. The idea that we propose is caching the IR instead of the machine code, differing optimization to make the IR reusable, and applying the optimization after the point of reuse so that we can still benefit from the performance improvements of VM-specific optimizations. And finally, deferred optimization may reduce peak performance, but it could potentially improve the warmup curves for some of these workloads. Thank you for your attention.
What are your thoughts on using this in like a tiered compilation strategy where you use the cached code initially while the other code is being compiled in the background and optimized more aggressively?
Yeah, sure. That could work. Yeah, we didn't try. I think it could potentially work but of course we would really need to be able to compile it much faster than compile it from the cache much faster than it's actually compiled from scratch.
Any other questions?
It's like a naive question, like what kind of optimizations that are invalid in the future? And in that case, why you need that optimization?
Okay, so what I mean invalid in the future, so if you have like a static final int, basically field, which has a value 4 in some run, and in another run it has a value 5. So like sometimes for if you take a particular static final field, some of them they have the same value in all the runs, but some of them the value can change. So like ideally, if you could somehow recognize these fields that the value changes and those fields that the value doesn't change, then you could defer only the optimization of those where the value changes. And this is not necessarily limited to fields, but in general.
Are they common in this, like for this type of optimization paths?
I'm not sure what you mean, sorry.
For those invalid transformation, right? And are they common in this? I'm not expertise in this. I'm just curious.
Okay, so what I mean by the transformations that are invalid is basically that in the original run where the code was compiled, the transformation is just fine because it leverages some state that it got from the VM, that the compiler basically read something from the VM and it was valid to do some transformation.
Okay.
But in the future, when you rerun the VM, then something in there could be different. Perhaps an address could change. So if you do the same transformations, then that would be invalid.
Okay, thanks.
Sorry, Andre. Thanks. Just two questions, actually. One, do you have an idea? You showed us peak slowdowns and peak performance, but is there an idea that you can get for actual saving on warm-up for each of these?
Yeah, I do not have the actual data prepared, but this actually depends, of course, where we cache the IR, but in GraalVM, the potential savings actually depend on the size of the method. So for small methods, the savings are actually smaller. And for very large method, the savings could be 10x or more. This is because basically at the beginning, the compilation time, like it scales, basically the complexity is bigger in terms of the size of the IR and nested loops. But after this point, the backend of the GraalVM compiler is usually faster. It's usually faster. Yeah, so the savings, they depend on the size of the compilation unit. The smaller it is, the smaller the savings. But for huge compilation units, they could be substantial.
Okay, thanks. Question number two, if we've got time, Fred, is so that's on the warm-up, but also there's also a space trade-off here. Do you have, so based on where you place the boundary between VM-specific and generic optimizations, do you have a sort of graph or some sort of Pareto optimal curve that can show size versus speed up?
No, I do not have this. I mean, in terms of engineering, we do not have much room where is the ideal place to do the caching. So yeah, I do not have this. I mean, but there is usually just one place where it's reasonable depending on the implementation. I mean, and we cannot really move it easily.
Okay, thanks. Just
maybe we have a couple more minutes. I have one more question. So, what are typical warm-up curves for GraalVM? How does that look like, and how does this add or subtract from that?
Yeah. So the benchmarks that we run, right, like Renaissance and Da Capo, and also depends how we define warm-up. But on these benchmarks, some of them it's tens of seconds until it reaches peak performance. Yeah, but it's also difficult to define peak performance. So it tens of seconds for some of them, and for some of them it takes minutes. Usually after 5 minutes, most of the benchmarks that we have, they should be warmed up.
Thanks. So let's thank the speaker. Okay, so the last talk in this session will be David Meese and Daniel Franklin from the Toronto Metropolitan University, and they'll be talking about the inline code generation in the Smalltalk language.
Okay. Oops, not what I wanted. Sorry. Sorry about that. I did not realize I had it set that way. Okay, so this is very preliminary work on inlining, and so this is work with my my graduate student. So, oops, sorry. So this audience doesn't really need too much education on what inlining or why we would inline, but so in particular, Smalltalk is very relevant here. So Smalltalk is full of sends. There is nothing in Smalltalk other than assignments and return other than sends, and so sends become really critical. So I want to inline to obviate the need for those. Access variables more efficiently. And in modern architectures, there are lots of registers. And if your methods are all very small, then you're not using most of those registers most of the time. So, and larger bodies of code obviously create more optimization opportunities. So there's kind of a hierarchy of need for inlining. So C compilers, for example, people inline, but it's not that critical because all of the calls, apart from function pointers, are essentially direct branches. So the hardware can do its look ahead, and there is no slowdown in calling a method, or very little slowdown in calling a method. Essentially just have to save the return address. Then we go to languages like Java or C++, where we have vtables, but they're static. So most of the calls to methods will incur a slowdown because there's an indirect branch, and that indirect branch will stall the look ahead, but otherwise they're relatively straightforward. But then we get to dynamic dispatch, which is Java and interfaces and dynamic languages. And here not only do we have the pipeline stall of the indirect branch, but we also have the slowdown of doing the calculation for the send or the call. So Smalltalk is dynamic, and so it has all those dynamic dispatch problems, but it also has some are social aspects, like very small methods are encouraged and the hierarchy is heavily used. But there's also fundamental aspects, which are that there are no control structures in Smalltalk. Everything is a message send. So control structures are message sends just like everything else. And also, Smalltalk has non-local returns, which is a very rare construct, but they are used fundamentally in the control structure. So this is very critical for Smalltalk. I won't go through the dispatch mechanism. It's what you'd expect, but there's we go up the hierarchy trying to find the appropriate method, and then we dispatch to it. So this is the same as Java, except in Java, because it's a statically typed language, the decision about whether something's going to be does not understand, i.e. a syntax error or a semantic error in Java, and the offsets are all statically determined. So in Java, when you send a toString message or call, that's in object, which means it's going to be at a fixed place in the dispatch table, the vtable for whatever class. So this makes it relatively fast. You incur the pipeline stall of the indirect branch, but otherwise it's very, very fast. So there's lots of work been done on this. Deutsch-Schiffman dispatch has been used since the 80s. And what this is that there's a bunch of special control flow selectors. So if true, if false, if nil, if not nil, etc., while true. And these are all important because there is no control structure in Smalltalk, and so it really matters that these operations be recognized. And so those are actually compiled by the compiler not to be sends, but to be explicit code. And the problem with that is, to be semantically pure, you have to handle something, especially when it isn't actually one of those. And so that complicates things significantly. The other problem with it is it's only specific things that are handled that way. So everything else we have to inline in a more general way. And caches are the way that this gets resolved. And so polymorphic inline caches have been in use since the 80s, and particularly heavily used in Self and subsequently JavaScript. And Self and JavaScript have per target dispatch tables. So in other words, when you have a particular structure that in JavaScript and Self essentially gets compiled into a class, sort of a hidden class, and then the sends to that class are going to be compiled for that class directly. This isn't traditionally done in most Smalltalk systems, although it is in the Smalltalk system that we're working on. And inlining is almost exclusively handled with native code JITs. So when people talk about inlining, they're thinking about native code JITs. What's new in Zag? It's a new Smalltalk implementation. There's a bunch of reasons why we're doing this, but one of the aspects of it is we have two execution models. One is the threaded execution model. This doesn't mean hardware threads. This means indirect jumping. And that's used for debugging. And then we have native implementations for speed. And the transition between these is seamless. So you can be in the middle of something, you have to debug, you can be executing native code, and when you start the debugger, it basically says, when I return from this, I will be in debug mode, and so we can stay in debug mode as long as we want. So we want these two versions to be semantically the same so that we can actually debug the code. We compile methods to concrete classes just like Self and JavaScript do. So what this means is that Self and Super are exactly known in most cases. So that means that when we see a send to Self, we know exactly what that is. Whether the corresponding method is above us or in this class, it's going to be compiled for this. The Zag model is what I call on-demand compilation rather than JIT, because in my mind, a JIT compiler will look at, as you've just heard, all the sort of context that's available in the VM at the point that we're compiling, rather than, in our case, we're just looking at the receiver of the message. So when we're compiling it, it's compiled for a target class. And there's a version of tiering here. So we first of all compile for threaded version with no inlining, and then we can do various other alternatives after that. So inlining. First is we have no ad hoc selector inlining, so if true or false, not handled specially. Inlining is semantic. In other words, it happens entirely at the intermediate level. And so it's debugging and the native are the same code. We do inlining breadth first, so basically we have our intermediate and then we go looking through the current version of the intermediate for opportunities, inline, etc. And this means that we can be more intentional. Because we're doing it at the intermediate level, that can be more intentional about the inlining. And so we can filter this in various different ways. The first is we can do n breadth first inline passes. We could maximize the number of inlines that we're wanting to do to minimize code or manage code explosion. We could also do things like inlining until all the block closures have been inlined that are possible. So that would get us most of the performance. So now we'd be back to a language more like JavaScript, I guess, in that the data structures will all actually be in code rather than in sends. We could also inline just code that had block closures as parameters. And we could also do incremental inline. So we could inline partially, sort of referencing the previous talk, inline partially, and then at some later date say, okay, it's worth doing 3 more rounds of inlining to get optimum code. This is actually the focus of the paper as I originally submitted it, which was the various opportunities to inline. Most of these are fairly typical. The most interesting one, I guess, is the 4th one, because Smalltalk doesn't have any loop structure. So traditional small talks handle that by recognizing while true and a couple of others as, oh, that's a loop, I better translate it that way. But what we do instead is we recognize tail call recursion, so, or tail calls generally. And so if when we're inlining, if we have a tail call that is to something that we're currently inlining, then we turn that into a branch. So this means that we don't have to have any special handling whatsoever to handle loops. We just have tail calls. And the fourth or third from the last one, if it's a value message, then basically we're just going to inline the block closure at that point. Conclusions, there are advantages to semantic inlining, and we don't have any execution benchmarking results yet. We will at some future point, at which point we'll come back and report this. And Zag Smalltalk is, oops, actually that's the wrong, that will send you to the wrong place. Sorry, we moved it. So it's Zag Research. So if you just go to Zag Research on GitHub. Sorry about that. So any questions? Oh, I should mention my university is hiring, my department is hiring. We have lots, like 8 open positions. They won't all be programming languages by any means, but if you are a PhD student or you have a PhD student who's about to graduate and would be interested in teaching in Canada, send me an email.
I was puzzled about how, supercalls are always static, but self is usually dynamic. How can you make those precise?
Sorry, because we compile for a particular class, so if we were compiling, I don't know, anyone, for example, which is a message that extracts just a sample value out of a collection. So the default version of that just actually uses do and returns the first value it finds, but there are subversions. So if you had a subclass, actually that maybe isn't the best example. If you have a subclass of something negated, okay, there's a simpler one. So if you send a message to a small integer to negate or negated, it will actually the code is actually in integer. It's not in, or it's actually in number. It's not in small integer. So it will be compiled into the dispatch table for small integer. So it'll be compiled, and now we know that that is self. Self is small integer, and so any reference to it we can handle. And also, if you, it's very common in Smalltalk to have virtual methods that send messages to self, but those are being compiled for the target class, so we'll actually have the right self in all those cases.
Thanks. Follow up on the previous question. So does that mean that you're specializing basically for the target or for self? So basically an overloaded or like an inherited method that it's inherited in a class chain of depth n will have n implementations?
No, we would have it just for the ones that you actually sent messages to. So what happens is we start off with empty dispatch tables. The first time you send a message to a particular class, we see it's not there. We go off, we find that, we go through the semantically appropriate thing to do that, and then we compile it for that class. And so now everything is known about that. In that compilation, everything is known.
Right. Okay, thanks. So question on the tail call optimization. So basically, so that it seems like you instead of tailoring or like looking for specific known control structures, like if I implemented my own bespoke control structures in SAG Smalltalk, I would get like the native performance, let's say, of a while in a classical Smalltalk.
So because there are no ad hoc selectors, you get maximum performance regardless of.
Right. And do I get sort of? I mean, this is always hard to do. But would I like get the same kind of performance as with the sort of the hand rolled optimizations for while loop and such?
Yes, exactly. So we actually rewrite while true. If you look at most Smalltalk implementations, they just say while true because they know that it's actually going to be compiled somewhere else. The only time you'd end up there would be if you did a perform. But for us, while true is rewritten to be a tail recursive implementation, as is one to or to do, for example, in small integer.
So the lazy specialization seems like really cool. Does that mean that if you update a method, you have to effectively empty the vtable of that class?
Track of all of the compiled code that knows about this implementation. So if we change something way up in the hierarchy, yes, lots of methods could be, but we just remove from the vtables, and then the next time the message is sent, we'll recompile it.
Do you also de-optimize them on the stack too?
No, they don't exist on the stack in that sense.
So if you have
I see what you mean.
Yeah, you have a specialized version that's executing.
No, we haven't thought about that. Perhaps we should.
Okay, we're pretty much have time, so let's thank the speaker again. So that concludes this session. So we have a 30-minute break, and then at 11 there'll be a keynote in this room about the CPython So we're going to have a real treat for our keynote. So there's this language called Python. There's a reference implementation for Python called CPython, and it was intended to just be a reference implementation, but everyone came to rely on it, so everyone's using CPython for their Python code, pretty much. There are other implementations, but they're much less used. So 4 years ago or so, they started a team at Microsoft called Faster CPython that was intending to just accept that people use this reference implementation and look at how to make it faster. Brandt has been working on this team for the last 3, 4, 5 years, and he's a core developer of the Python programming language as well. They've been working on various things to make CPython faster, and he's also been working on some pattern matching features that shipped in Python 3.10. So let's introduce our speaker and enjoy this.
Hello, everybody. So my name is Brant Bucher, and today I'm going to be talking about basically how Python executes your code and how a bunch of us have been making that faster in recent years. So buckle up. Before we get started, a little bit about me. So my name is Brant Bucher. I first started using Python when I was studying computer engineering as an undergrad at UC Irvine, and I never looked back. So I gave up hardware and I was all in on software because I just loved the language so much. I started contributing my first code pretty quickly after that, and I've been involved in Python core development since about 2020. My pandemic project was adding structural pattern matching to the language. Shortly after, I joined Microsoft's faster CPython team, or the CPython performance engineering team, where I work now, and we've just been focused on making the reference implementation of Python, CPython, faster for everybody. Our work quickly bore fruit, so in 3.11, we were able to show a 25%-ish speed improvement over the 3.10 interpreter, and in recent years, we've been working on actually adding a JIT compiler to CPython, which has been a big, fun, exciting, really challenging project, and so I'm going to share a little bit about that today. So what is Microsoft's CPython performance engineering team? You may have heard of it referred to as the Faster CPython project. This is a larger initiative that is spearheaded by the 6 of us at Microsoft who are on the core team, but we collaborate with people all over the world. So in addition to the people on our team, we also work with people at Snowflake, ARM, and also the National University of Singapore. You know, it's not a closed team or anything, so if anyone wants to get involved, there's a lot of really, really cool stuff that we're working on. So if anything seems interesting today, please reach out and get involved because it's really, really exciting work, and it is an opportunity to have like a serious impact on real code. All of our work happens in the open, so all the people on my immediate team are committers to the CPython code base. We have a repository on GitHub called fastercpython/ideas. This is our public issue tracker. While we use the CPython main issue tracker for works in progress, this is kind of where we just kind of throw ideas out for early discussion and share papers and things like that. So enough about me and my team. What is Python? Well, Python is this programming language that is older than me. It's very high level. It's very widely used. It is a dynamic, interpreted, object-oriented language that features automatic memory management and a bunch of deep introspection and metaprogramming features. So all of these things are making life very, very nice as a Python programmer because you can do a lot, but you also don't need to do a lot. But as language implementers looking at this, this is terrifying, right? Like all of these things that make Python so easy to use and so successful are also the sort of things that make it very, very difficult to optimize effectively. Specifically, just to give some ideas, most objects, as with many dynamic programming languages, most objects have arbitrary mappings of attributes, and these are actually exposed as dictionaries at runtime. And they don't just need to be string attributes, these are normal dictionaries. You can throw anything in there. You can store references to them, you can monkey patch them at runtime. It's a nightmare. Bytecode itself is a runtime object, and people do crazy things with this, building their own code objects or introspecting existing code objects. Frames themselves are runtime objects, and you would not believe what it is possible to do with a running Python frame. You can assign into the locals, yes, but you can also change the line that is currently executing. This is how like the jump command works in a debugger. You can jump in and out of dead code. Even attribute and global name accesses and even stores to local variables can execute arbitrary code. So reasoning about the state of the world is really, really difficult to do, even in limited context. And even simple operators go through incredibly complex double dispatching. If you think you know how Python's operator resolution works, I can almost guarantee you that you're missing some details of how it actually works. Like if subclassing isn't part of that mental model, then it's wrong. And finally, as I mentioned, a debugger can be entered anywhere and basically do anything. So this is kind of the context we're working in. And again, this is all great to see as a Python programmer because you can do all sorts of crazy things and debugging your code is really, really powerful and easy. But at the same time, for the language implementers, yeah, these features are like kind of fun or whatever to expose to users, but when it comes time to actually have performant implementations, it's actually really, really difficult to make any progress, especially on something that's this widely used and this old. So that's Python as an actual programming language. Let's talk about CPython though. CPython is the reference implementation of CPython. It's written in C, which is where the name comes from. And it's used by the vast majority of Python programmers, so much so that for the rest of this talk, I'm just going to use the terms Python and CPython interchangeably. It is reference counted, augmented with cyclic stop the world GC. This is relevant because people have become very, very used to and reliant upon the prompt reclamation of acyclic garbage. And it has an incredibly rich ecosystem of third-party C extensions, for example, NumPy and Cython and other libraries like that, things that we cannot break, or if we break, we need to provide clear upgrade paths. It's maintained by a few dozen active core developers. I'm lucky enough to be one of the few who's actually paid to work on CPython full-time, but for most people, it's either a retirement project or nights and weekends. Maintenance is also a concern because we have a finite amount of developer time, and it's very, very valuable. And of course, Python, specifically CPython, is free and open source, so you can check out the code here on GitHub, and there's a full issue tracker where all the actual work in progress happens. So with that context, let's talk about optimizations. So typically when you are optimizing a programming language, the steps look like this. First, you build an intermediate representation, then you check the types, you optimize based on those types, and then you compile. Obviously, for dynamic languages, this type checking step needs to be replaced with a profiling step. This is something that we've been doing for a very long time to optimize languages like JavaScript. And so this is just-in-time compilation, right? And it means deferring a lot of the traditional compiler optimizations until actual runtime rather than statically and ahead of time. So a lot of the kind of traditional optimizations that we're used to seeing, while some of them can be applied in sort of limited measures to the actual static bytecode itself here on the left, many of these actually just need to be deferred till runtime to actually be of any use. And even amongst the ones that we can do statically at, in the bytecode compiler, even for things like dead code elimination, again, it's very, very limited because debuggers can jump into dead code and they can assign to local variables on any line. So even propagating constants is like super fraught. So again, this basically means that we need like very clear runtime context in order to build anything that's performant at all. So we're just going to walk through basically how recent versions of CPython have actually executed my Fibonacci function here. This is a iterative Fibonacci function. It's pretty straightforward. We basically take a parameter n, assign local variables a and b to be 0 and 1. We loop n times, and we're just adding a and b together repeatedly. Specifically, we're going to focus on this hot inner loop where the function spends most of its time. So the bytecode for this loop looks something like this, which I'll show in the center, and then we'll just walk through how this executes. As many of us know, CPython is a stack-based virtual machine, so I'm going to show the stack there on the far right. So when we enter this loop, we start with an iterator already on the stack. And basically, this first instruction in the bytecode stream, the for iter instruction, is responsible for advancing the iterator and pushing the result to the stack. So this is a somewhat generic operation, and there are lots of generic operations in Python because it is so dynamic. So things like iteration, attribute lookups, method calls, even normal operators can follow many, many different code paths and do many, many different things. You can have an add operator that formats your hard drive if you really want to. In this case, there are lots of different things that we can iterate over. And so that's where specialized bytecode comes in. And this is where we were able to get a lot of the performance improvements that we saw in 3.11. Basically, like I said, there are many things that we can iterate over. We could be iterating over lists or tuples or generators or a custom iterator object. But a very common thing for people to iterate over, and what we're iterating over in this case, is a range object. And so we actually have a bytecode specialization for 4-iter range. And the way specialized bytecode works is basically these generic instructions at runtime will listen to the types that they're operating upon and replace themselves with self-modifying code, basically replace the bytecode instructions in place with a specialized variant. This contains a couple of guards to make sure that the assumptions hold, in this case to check that we're still iterating over a range object, and then it contains a fast path for actually doing the work. And in this case, the work can be a lot faster because we don't actually have to go through all the dispatching involved in Python's iterator protocol. And so basically, after that's done, we store the result in the fast local variable, in this case, just the underscore. And then we load 3 more fast local variables and push them onto the stack, B, A, and B again. Then we hit our binary operator instruction, which is responsible for adding these 2 values together. Again, things like addition are incredibly kind of complex in the way that they actually dispatch at runtime. In this case, we're just adding 2 integers together. And so we will specialize for the common case of binary op add int. So this is something we can do a lot more efficiently. Now, it's important to realize that this specialization actually adapts to the code over time. So as the program undergoes phase shifts or the context in which the program is running changes, the specializations will adapt too. And this is really important, and we'll see why later. But just to give you an idea, if I were to enter a debugger inside of this loop and replace A and B with strings, for instance, this is no longer integer math. This is now string math. And so the guards that actually check that the specialized instruction is operating on integers will repeatedly fail. And after doing so for a small period of time, the instruction will respecialize itself into, in this case, binary op add Unicode. And so you can see that sort of as your program undergoes shifts, the bytecode actually adapts and changes with it. And specialization is super cheap. Since a lot of the work that we're doing to figure out which specialization we should use was already going to happen in order to dispatch the operation itself, it's almost free. So we specialize the second time any bytecode instruction is hit. Basically, in our mind, there's run never code, run once code, and run many code. So specialization is cheap enough that it just makes sense to do. So finally, after we have added our 2 integers together, because we haven't entered a debugging session, at least not yet, we pop 2 results off the stack and store them in fast local variables. And by then, we hit the bottom of the loop, the jump backward instruction, and we're back to the top. So basically, that is how Python has executed for quite some time now, a couple of years, ever since we landed specialization in 3.11. But where we're going with this is basically higher tiers of optimization. In this case, what we call micro-op traces. So basically, our goal is to build a tracing JIT compiler. And we've already made some really great progress towards that. So what are micro-ops? Well, to give you a little bit of background, we've made a recent change in the last couple of years for how Python's interpreter is actually defined. Previously, we had a bunch of handwritten, like actual cases in a big C switch statement. Recently, we've made the change to actually generate all of those cases from a DSL. And that frees us from a lot of the kind of tedious work of actually needing to do all of the bookkeeping of like adjusting the stack itself or pushing and popping items from the stack and doing like frame pointer updates and, instruction pointer updates on the frame and things like that. So to give you an idea of what that looks like, this binary op add int instruction in our DSL is actually defined as the concatenation of 3 other operations. In this case, it's first guarding that the top of stack item is an integer, so we have a micro-op for that. Guarding that the next item on the stack is an integer, so we have a guard for that. And then finally, the meat of the instruction, binary op add int, which actually pops those 2 values from the stack, adds them together, checks for error, decrements their reference counts, and then pushes the result. Again, you can see that I've sort of had this declarative form where I say what the stack effect of an instruction is, and so all of that is generated automatically. Now this is nice because when generating the binary op add int instruction, we just sort of concatenate the bodies here. But it also means that we now know the different components of the instruction. In addition to this, we also get nice code reuse because it should be pretty clear that the toGuard instructions can be useful for other instructions as well. For example, if I'm multiplying two integers or subtracting two integers, we can use these same ops. So while we are actually generating the bytecode interpreter itself from this DSL, we're also statically analyzing the DSL, and we can use that to generate a lot of additional metadata. So for example, a table that maps the base bytecode instructions to their component micro-ops. And we can do this for every single instruction. And this makes translation of our collected traces to kind of a lower level, more optimizable IR completely automatic. So you can see here that once we've projected our trace through the loop, it's just a matter of basically walking over our trace and looking up each instruction in this table that we've already generated automatically and basically just concatenating all of the implementations together. And so this is really nice, and so it happens very easily and very cheaply. And one thing I forgot to mention is that when we project the trace through the loop, we're actually stopping the program and basically looking ahead and seeing, okay, where are we actually going to go? So we're not recording a trace as the interpreter is running, we're instead stopping and following it. It's at this point that we do some basic inlining. Since our call specializations have information about where we're actually calling to, inlining becomes pretty simple. And we also keep track of the most recently seen directions of branches so that we can follow branches through the trace. Again, in our Fibonacci example, it's just a straight trace through the loop, but it's nice because we just get this sort of inlining and branch tracking for just based on the profiling data that we are already collecting. So once I have this micro-op trace, we actually want to do something with it, right? So starting in 3.14, which is due out in October of next year and is currently in active development, we start optimizing these traces. And we have a basic optimizer that's in place now. It performs some sort of lightweight optimizations, but our plan is to really build upon this in the coming year to do more kind of meaningful transformations. So just to give you an idea of sort of what we currently do and what we hope to do, we do a number of passes over this linear sequence of micro-ops. But sort of the most interesting and the most powerful of these is an abstract interpretation. This abstract interpreter that we loop over the micro-ops is, you guessed it, generated from that exact same DSL. So we are actually able to generate the abstract interpreter and have default cases for many of the instructions, and we can handwrite cases for the ones that we want to optimize more aggressively, which is great for developer productivity. So you can see here that we'll basically just loop over each of the instructions, and we can keep track of sort of the symbolic values of what we're operating on. As we encounter things like guards, we can narrow the types of stacks and locals, and we can even keep track of sort of what different expressions that we have encountered along the way. It's during this that the current implementation will do some like lightweight guard removal. So if we're guarding the same value twice, we can remove it. We also promote some like global loads and local variables to constants at this point, and we remove some ref counts. But again, a lot of this is still in the early stages, and we hope to do more aggressive stuff later. So at this point, in addition to those changes, we have another pass that will basically do a lightweight escape analysis and remove some bookkeeping that's unnecessary. For example, to check that our optimizations are still valid, or to set the instruction pointer on the frame if we might escape and need to be able to form a traceback or something like that. But again, in the future, we hope to do more powerful things. One kind of just obvious example would be being able to identify guards and hoist them out of the loop. So that way they're not in the actual hot path, which again allows us to reduce bookkeeping even further. So once we have that optimized micro-op trace, basically the way that we handle tiering up from the base interpreter into our new micro-ops is, again, using specialization. So in this case, we can take our jump backward instruction and specialize it into an instruction that we call enter executor, which will basically start executing our optimized trace of tier 2 micro-ops. So how does this do? Well, obviously, we don't want to interpret these things long term, but we do have an interpreter for them. just because we needed to have something working to make sure that everything works correctly and that we can debug it. So actually, when you enable the micro-op interpreter, and after all the optimizations that we already perform, it's about 20% slower, which is like a huge letdown, right? Like we've got all this work, we've got like the beginnings of some cool optimizations, but a big part of that is that we're introducing a ton of interpretive overhead. You'll notice that the trace of micro-ops that I was left with was actually much, much longer than the original trace of bytecode instructions that I had. And the bytecode instructions are already specialized. In addition, the name micro-op is sort of deceptive because these instructions are way, way huger than the base bytecode instructions. They contain much wider operands and cached values. And they have much more like debugging information and de-optimization information. So decoding them is actually a lot more complicated. In addition, there's a lot more of them, so the interpreter loop itself is a lot branchier and more complex. So that naturally drives us towards just-in-time compilation, which is where we were kind of headed the entire time anyways, but is now even more justified than before, because we don't want to do all this work and then now get a 20% slowdown. So to recap, we have a couple of technical goals that we hope to achieve with this. Basically, we want to remove the interpretive overhead that we've introduced with the micro-op format, and we want to statically compile these optimized traces. And this is being done for a couple of different reasons. Basically, we want to reduce indirection by burning in constants and caches and arguments and things into the machine code itself rather than having to decode it in this interpreter. And we want to move data off of frames and into registers. If you noticed, the micro-op format doesn't actually change representation at all. We're still pushing and popping things from a stack and storing and loading things from local variables. Finally, we want to bring hot code paths in line. So rather than having a generic interpreter with a bunch of cases that are kind of in a tangled control flow graph, we'd rather unroll that into a linear sequence of code. Now, given the context that we're working within with CPython, we also have a couple of like realistic goals about what we can accomplish, right? So like, in order to set ourselves up for success, in order for this to be feasible for CPython, we need to have broad platform support. Python is very widely used, and it's widely used in a lot of different places by a lot of different people. I don't think it would be necessarily successful if this JIT compiler were only able to work on 1 or 2 operating systems or on 1 hardware architecture. In addition, we want to have as few runtime dependencies as possible. Currently, if you download a Python interpreter from python.org, everything just works. You don't need to also install a compiler toolchain nearby or build LLVM or whatever for your weird platform. And finally, and most importantly to me, it needs to have low implementation complexity. Like I said, Python is overwhelmingly maintained by volunteers, and so maintainer time is very, very valuable. We're willing to leave peak performance on the table in order to have something that's maintainable and that people can feel confident fixing bugs in and extending into the future. And when adding language features, it's not a significant time sink for them. So again, these are very much in conflict, right? Like we want to be able to make things faster, but we also are kind of tying our own hands behind our backs with the situation that we find ourselves in. And so one sort of really satisfying solution to these sort of competing goals is this thing called copy and patch compilation. It comes out of this paper from Stanford by some very creative people who also have great taste in keynote speakers. If you want to read the paper, then I highly recommend it. There's also a great accompanying blog post by one of the paper's authors, Haoran Su. It walks through basically using this copy and patch technique to build a JIT for a Lua implementation. So if you don't know how just-in-time compilers works, read that blog post, you'll know how JITs work. But in a nutshell, it's a way of automatically turning a C interpreter into a fast template JIT compiler. We have a C interpreter, we want a JIT, sounds promising. Even more promising are the numbers quoted in the paper. Compared to a WebAssembly baseline compiler, in this case Liftoff, copy and patch has been observed to have 5 times faster code generation and about 50% faster code overall. So not only are we JITting code faster, the code that is being JITted is faster as well. So it's strictly better. Compared to a traditional JIT toolchain, for example, LLVM with a low optimization level to keep things snappy, it's 100 times faster code generation and still faster code overall. And finally, as sort of an upper bound on the sort of performance that you can expect from this sort of thing, compared to an optimizing JIT with handwritten assembly, in this case Lua JIT, a copy and patch Lua implementation has been observed to be faster on some benchmarks and only about 35% slower overall when you take all benchmarks together. So this is exactly what I'm talking about when I'm saying we're willing to leave some peak performance on the table in exchange for what seems to be a great JIT implementation. So how does this work? The idea is really, really cool. Basically, I'll start by asking a question. If you have a sequence of bytecode instructions and you want to translate them to machine code as quickly as possible, how would you go about doing that? Well, it might look something like this. At runtime, you walk over your sequence of bytecode instructions, and then for each one, you copy some static precompiled machine code into executable memory, and then you patch up instructions that need to have runtime data encoded in them. So this would be things like jump targets or operands, that sort of thing. Now, when you look at these two steps, you'll realize that this sounds a lot like something that we already have, which are relocatable object files. So I could just as easily say, when linking or loading an ELF file, first I want to copy some static precompiled machine code into executable memory, and then I want to patch up the instructions that have the runtime data encoded in them. In this case, these would be external relocations, relocation records for symbols that you're linking against. And so the way copy and patch works is pretty elegant. Basically, if we're starting with the case for our load fast micro-op here, the instruction itself is pretty straightforward. We basically pull the local off of the frame by indexing into its locals array with our op-arg. We increment the reference count of the value that we're loading, and then we push it to the stack. We want to compile this instruction in isolation to machine code automatically. This is how we do that. Basically, we take the body of that instruction and we put it inside of its own C file, inside of kind of a dummy function that we're going to throw into a C compiler. Now, obviously, this isn't going to compile on its own. We're accessing local variables that don't exist. For instance, we need to get the frame from somewhere. Now, the frame isn't like some sort of constant. It's going to be different every single time that our JITted instruction executes. So we actually probably want this thing in a register. Thankfully, we can kind of force it into a register by just saying, oh, it's a parameter to the function. And so when we enter this block of machine code representing the body of the function, it will expect the frame to be in that register. You can kind of see where I'm going with this. Similarly, the stack pointer. This is just like the frame. It's going to be different every single time that our code executes. And so we can throw that in a register as well. However, with the op-arg, we have something a little bit different. The op-arg is going to be effectively constant each time we JIT the code, but we don't really know it when we're building the template itself. So the way copy and patch actually handles this is by just sort of saying, okay, let's just magically insert the op-arg there and move on. So let's just ignore the problem for now. Similarly, you'll notice that we need some way of basically transferring control flow to the next instruction in the trace. So again, we're just going to hand wave that away and just say, okay, we just have some way to magically run the next micro-op. We'll just call into the next micro-op at the end of the function. So how do we deal with these two kind of hand-wavy placeholders that we put in here? Well, as I've alluded to, we can actually use externs to do this. So by declaring both of these extern, basically what the C compiler is going to do is it is going to leave holes in the generated code where the information needs to be patched, and it will actually give us relocation records that say where those holes are and exactly how to patch them. So you'll notice that I have my op-arg here, and a hole will be left for that. And then we also have the call to the next instruction, which here is expressed as a continuation. You'll see we have that must-tail attribute, which is a unique feature of Clang. I think GCC supports it now too, I think because of us. But it's really nice because it basically guarantees that rather than being a call, this will be compiled to a jump. It basically guarantees that you'll get a tail call here, which we need for correctness. So if you take this thing and throw it into your compiler, what you'll get is an ELF file that looks like this. And this has everything that we need to JIT our load fast instruction. It has all of the bytes that we want to copy. So you can see here they're highlighted in blue. And it has all of the holes that we want to patch, highlighted in red here. And at the bottom, our relocation records tell us exactly where those holes are and how to fill them. Now, we could just move on with this as it is here, but we actually have the opportunity to do some very localized optimizations. So we don't want to be handwriting huge amounts of machine code, but when we see opportunities to improve the quality of the machine code in very clear and simple ways, we'll absolutely take advantage of that. So for instance, you'll see here that where we're loading the op-arg, we're actually doing so through a layer of indirection. That's because we need to load a wide 64-bit value for our relocation, but really the op-arg will be able to fit in 32 bits just because of our micro-op format. So we can actually relax this load. Instead of using an indirect load to get 64 bits, we can just encode 32 bits in the immediate. This is a very standard sort of a load relaxation that things like linkers perform. Basically, at runtime, if something can be encoded more efficiently, different transforms like this are very well documented. Similarly, we have this jump to the continuation at the very end of the instruction. This is a full 64-bit indirect jump, which is a little bit overkill because we know that the jump that we are going to make is going to be nearby in the code. So we can make this a 32-bit immediate jump instead. Similarly, you can see that after those transformations, we've introduced 2 no-op instructions at the very end and very end of the trace, so those can be removed as well without too much worry. And finally, we now have this zero-length jump at the end of the trace. Remember, when we're actually emitting the machine code itself, we're going to lay out one instruction directly after the other. So this jump to the next instruction is going to be a zero-length jump, and we can just wipe it out safely. And so once we have that, we can actually just parse out all of this information and basically write it into a static C header file and generate this function here. This is a function that if you call it, you can JIT a load fast instruction. All you need to do is pass it a buffer and the instructions so that it can retrieve the op-arg. This is really, really cool, and it's really, really fast. It actually takes more time to allocate the memory for a copy and patch JIT compiler than it does to JIT the memory itself. It's awesome. So another really, really great part of this strategy is that it has incredible platform support because we're able to build on, or we're basically able to outsource all of our kind of nitty-gritty, low-level optimizations to a optimizing C compiler at build time, in this case LLVM. Another thing I forgot to mention is that when we are compiling these templates, we can do so with a very high optimization level because we're not bound by runtime constraints. So in addition to x86-64 on all the platforms that we care about, we even support 32-bit Windows and 64-bit ARM on all of those same platforms. This is pretty much most of the places that Python runs. There are some more esoteric platforms, but these are absolutely the most common ones. And we can just support them out of the box with very little implementation effort on our part, basically just knowing how to translate those relocations. And so let's talk about the results. And again, these are sort of intermediate results because a lot of this work is ongoing. And we just recently landed the JIT compiler earlier this year. The current implementation has about 1,000 lines of build time Python code. So this is the code that handles actually taking all of the micro ops, putting them into sort of those dummy C functions, compiling them, parsing out the ELF, fixing up the assembly, and then writing it out into that C header file that we include when compiling the main interpreter. This is accompanied by about 100 lines of complex C. This is basically just a template for that dummy function that we sort of insert the opcode bodies into. And there is an LLVM dependency, but again, this is a build time dependency, not a runtime one. So users don't need to have this installed on their machine. It's only if you are building a Python interpreter, which is much less common, with the JIT enabled. At runtime, things are super slick. We have about 400 lines of simple C for the JIT loop itself. It's basically just looping over the instructions, allocating the memory, and calling each of these generated functions, one for each instruction. And we do have about 4,000 lines, and I should mention that C code is like simple, but it's like simple-ish, because JIT is never simple, right? We also have about 4,000 lines of truly simple generated C, and it really is just as simple as the code that I showed you on the previous slide. It's these function bodies that basically perform a mem copy and then a couple of basically writes into a buffer of bytes. And most importantly, no runtime dependencies. And so you can see here that we have taken all of this complexity and we've shifted it from runtime into build time, which we're absolutely happy to do, and out of C code and into Python code, which we like writing a lot more than C code. In terms of the results of the JIT itself so far, you'll remember that when we had the micro-op interpreter enabled with the light optimizations that we already perform, it's about a 20% slowdown. With the sole change that rather than interpreting the micro-ops, we JIT them, we are now back at parity with the base level interpreter. And we're not even doing most of the fun stuff that we hope to do. a big reason why we haven't actually focused work on improving the JIT code itself, and I'll get to some of our plans for that, but a big part of why we haven't actually focused work on that itself is because currently our tracing implementation needs a little bit of work. According to statistics gathering, we only run about 6% of our benchmark code in the JIT. So obviously, if we were to make the JIT twice as fast, it would barely show up on the headline number, right? And this number is actually kind of lower in practice because our benchmarks only spend about a third of their time in the interpreter loop anyways. They spend a lot of time in GC and library code and stuff. So we needed to get this number up. As of today, this number is more like 65%. So we've been putting a lot of effort into making sure that we can basically detect and translate more types of hot code at runtime. And by the end of the year, we're on track to get this to about 91% with the handling of a couple more edge cases. Now, another interesting number is the amount of memory overhead, right? So when we first landed the JIT and we were JITting 6% of the code, we had about 10% increase in total memory usage at runtime. Now that we're JITting 10 times as much code, memory usage is half that. So some of the people that we've been collaborating with, specifically at Snowflake and ARM, have been working on actually improving the memory usage of our JIT code. And the results are actually quite dramatic. And the really cool thing is that this is actually sort of a high watermark because this is based on benchmarks which have a high ratio of code to data. In most situations where you would actually be experiencing memory pressure, you would have a high ratio of data to code, and so this number would actually matter less since more data doesn't mean more JIT code. So with that in mind, let's talk about future work. Where are we heading and what are we working on? Most of this is for stuff that's going to ship in 3.14 at the earliest. 3.13 just came out, I think, last week. So it's stable. Go download it. Go try it. But 3.14 is where we're kind of focused now. So one thing that we're interested in is this idea of stack caching. And this comes out of a paper from about 30 years ago, but the idea still holds pretty well. It's basically a lightweight register allocation scheme for stack machines. So you'll notice that in our micro-ops, we are still actually incurring a ton of memory traffic to send data to frames and pull data off of frames, and those live out on the heap. So ideally, we would like to put as much stuff in registers as possible, because register allocation is a very important optimization. While we're able to rely on LLVM to do good register allocation within the body of a single micro-op, it's kind of on us to make sure that the information that flows between micro-ops is treated appropriately rather than it just being sent to and from memory whenever we decide we want to read it. So you'll see here that for my binary op add int instruction, we are basically just pulling two values off of the stack, adding them together, checking for error, decrementing the reference counts, and then storing the result to the stack and shrinking the stack. And you can see here that we're actually doing a lot of work on the stack pointer itself. Again, this isn't like the hardware stack. This is just a Python heap allocation sitting out in memory somewhere. So we want to reduce this as much as possible. Now, we've already kind of hinted at this, that when we want things to be in registers, we can actually just represent them as parameters to the function. So let's say that we want to cache the top of stack value in a register, which in this case would be a parameter that we take in from the function and pass to the continuation. We can now automatically generate two versions of this binary op add int instruction. One where the cache is empty, in which case the way we get our inputs doesn't change, but now we actually don't need to write the result back to the stack. We can just pass it to the continuation in the appropriate parameter there at the bottom. And then we can also generate a version where the cache is populated by a previous instruction. And so in this case, we're actually able to get one of the operands from the register, get the other one from the stack, and then write the result out to a register. And it's easy to see how this extends. We have lots of registers to play with, and so, for instance, we can have a cache state with two items, in which case the frame isn't involved at all. We take in both of our values as cached values, and then we send them out the door the exact same way. Now, this gets even more fun with this fancy new calling convention in Clang 19 called preserve none. This is super cool. So preserve none is a calling convention that has no callee saved registers. Now think about what that means. Basically, when we're making our tail calls, we are doing a lot of kind of pushing and popping and saving and restoring registers at the beginning and end of every function body. Preserve none basically says, okay, don't count on this function to basically save or restore any state. Just let it do its thing. It's going to clobber everything. What this does is it actually frees up a lot of registers for argument passing. So this is great for pinning things across tail calls, but we now have, on x86-64, we have 12 registers to play with. So the first 12 parameters that are passed to any function that uses the preserve none calling convention are passed in registers. On ARM, it's even more insane. We get 24 registers to allocate. And so this is basically a way of basically controlling the register allocation in the machine code between micro-ops without actually having to do anything other than just saying this parameter corresponds to that register and basically treating it like that rather than needing to be more machine specific than that. So this is really, really exciting, and it's something that we're going to be looking more into for the 3.14 cycle just because it's such an important optimization at this level. And again, we can build on top of our existing micro-op-like generation machinery where we can use the static analysis and the DSL and our ability to generate multiple variants of an instruction in order to do this. Another thing that we hope to improve is our trace stitching. So we already do some amount of trace stitching where basically we have several side exits corresponding to guards in the machine code or maybe branches not taken. Those warm up over time and project traces of their own, but the optimization information isn't very well shared between the parts of the traces. So we kind of lose optimization information across that stitching boundary, as well as the actual transitions themselves are incur a little bit of overhead. We're doing things like jumping through function pointers and adjusting ref counts and things like that. So kind of the future that we're hoping to move forward to in trace stitching is something like this. And I'll kind of leave you with one final example. So take my state-of-the-art FizzBuzz function. It's written not too well, but it works. We're going to see how we would like to actually JIT this thing piece by piece with our tracing JIT. So I'm going to use red to indicate hot code paths and blue to indicate cold code paths. And as we JIT more and more of this loop, those paths are going to change with time. So you can see here that initially the common case is the one where we're just printing the number itself and it's not divisible by either 3 or 5. So when we project a trace, when this loop heats up and we project our trace through the loop, it's going to look something like this. And after some light optimization, we're kind of have the basic path through the loop for this common case, which is great, but you can see here that we sort of have these side exits where we need to bail in different situations. When the iterator is exhausted, when the numbers are divisible by 3 and 5, and we need to take different code paths. One thing that we'd really like to be able to do is be able to actually sync information onto side exits. So you can see here that we have this dead store to S here that isn't actually used anywhere in this trace. However, it is just kind of a constant store. So what would be nice is if we could actually, rather than doing it here, move that store onto the 2 side exits so that it's out of the way of our main path. And so that we only actually perform that store after the fact when the time comes to actually deopt. Now, once we've done this, basically all's well and good. We're executing the hot code path using our JIT. And now we actually have kind of a different performance profile. Now the next hottest path is the one where we're divisible by 3. In this case, that side exit is going to warm up, and we're now going to project a new trace through the loop. And again, we can do the exact same thing here. However, we now have a lot more information from this sort of first pass of optimization. And since we've sunk the store to S onto the side exit, we can do constant propagation and some partial evaluation to basically reduce it to the minimum amount of work that needs to be done. Basically, just checking whether the number is divisible by 5, and then either printing fizz or syncing the store to fizz onto the side exit. And now we have the second most common path through the loop. And we can just keep doing this over and over again, where we sync this unnecessary work onto the side exit and propagate constants and do all of our cool optimizations as we work our way through the loop. And by the end of it, you'll see here that what we've actually JITted is a pretty good FizzBuzz implementation, and it's actually better than what the original code was doing. This is kind of the bare minimum amount of work that needs to be done, and because we were able to perform some relatively simple optimizations, basically our optimizer needs to know how to be able to propagate constants and add string constants together. Just by sort of sharing this information across traces, we are able to actually get something that's pretty good. And on top of this, if we are able to take all these traces that may have been compiled separately and periodically compact them into one kind of chunk of machine code, that can also result in efficiencies as well, because we won't need to be doing these indirect jumps and validity checks and all sorts of things. And once we've gotten to this point, the only thing left to do is wait for the exit from the for loop to heat up and continue projecting from wherever it happens to go next. So that's the trace stitching, and I showed here that it works for explicit control flow in the actual source code, but it also works really well for things like polymorphic code. Remember I said that our specializations will adapt to your code over time? Well, think about it. If we JIT the most common case, let's say you have a polymorphic attribute load or a method call. We'll go with a method call. So if I have a polymorphic method call, the most common one will be reflected in the specialization in the code, and we can actually inline that when we project our trace. Then, every time we call that one, it will actually stay in the JITted code, and we'll only deop to the base interpreter, the specializing interpreter, whenever the second most common method is called, or whenever other methods are called. And soon that will specialize for the second most common method, and we can JIT a trace for that. And so we're basically relying on the specialization to not only speed up the execution of the kind of base bytecode interpreter, but also to give us this profiling information that changes with time. And we can also use it to track things like branches too. But this works for pretty much any reason why we might branch in JIT code, including weird deopt events and global validity checks and things like that. So as I mentioned, we kind of take a holistic approach. So I talked about a lot of like hardcore VM stuff here today, but there's kind of a lot of different things that we focus on our team and in this Faster C Python project in general. In general, we care a lot about our benchmarks, so we're always interested in getting new benchmarks, especially ones that use like modern code patterns or language features. We also want to reduce reference counting overhead. You notice that we were doing a ton of reference counting all over the place still. So it's tricky to do because, like I said, people still rely on the prompt reclamation of acyclic garbage, which is frustrating to say the least. But like if we can prove basically through alias analysis or by knowing that we have safe types without crazy finalizers or anything like that, then we could actually start removing more reference counts because we spend a ton of time reference counting, especially in the interpreter loop. We've made some improvements to the object model over the last couple of years. Basically, most objects don't actually have a full instance dictionary until you ask for it. We kind of lie and say, oh, there's a dictionary here. If you ask for it, it'll magically appear for you. We did similar things for Python frames as well. Every frame used to be a full Python object that was reference counted and garbage collected and all of that. We now only create those on demand. So there are always opportunities to basically take these uncommon events and basically optimize for the case where they don't happen, but still have fallbacks for the case where they do. Another thing that we're excited about is what we call true function inlining. So while our tracing implementation is able to basically follow the flow of execution through a call site, we are able to propagate optimization information through that call, but we still push and pop a frame. So we don't have yet a way to actually like reconstruct frames on side exits and things like that. That's sort of similar to how we would sync stores onto side exits as well. Integer unboxing is always kind of like an interesting thing. We have a lot of kind of ABI trickiness in our main interpreter loop that makes this sort of non-trivial. Pointers can escape the interpreter in all sorts of really weird ways, and people can just query Python frames almost willy-nilly, especially from like C code that we don't necessarily control. So being able to do this in a safe way where people don't just get garbage pointers is pretty tricky, and it's frustrating because it doesn't work until it does, right? We are always looking for GC improvements. So I think we spend like something like 10% of our time in the GC, so small improvements there can actually have an effect on the headline number of how we're doing on our benchmarks. As well as work on concurrency and parallelism. So you may have heard there's a team at Meta that's doing a lot of really, really cool work to actually make it so Python can run with true parallelism in multiple threads. This is requiring a lot of changes to the core, and it gives us a bunch of big unknowns because while it's very much settled how to optimize dynamic languages in a multi-threaded environment, and it's very much settled how to optimize static languages in a multi-threaded environment. Optimizing dynamic languages in a multi-threaded environment is still kind of an open question. And so there's kind of a lot that we don't know there and that we're kind of curious to figure out. And who knows what else? Like, this list looked very different a year ago. It's probably going to look very different a year from now. Like I said, we're always happy to hear if anyone has ideas or wants to help contribute to this work, because the work is benefiting every user of Python, and Python is a huge code base with, trust me, a ton of inefficiencies. So thank you very much. Again, my name is Brant Bucher. I'm at Brant Bucher on GitHub. You can also reach me at brant@python.org. The developer division at Microsoft, where I'm currently working, is always hiring talented compiler engineers, especially for the C family of languages. So talk to me if that interests you at all. And thank you very much. And I think we have time for Q&A. Yeah.
Hi.
Yes, it's very quiet.
Hello. Yeah, okay.
Yeah.
So thank you for a very nice talk. I was wondering, what about if you're compiling to different ISAs like x86 or ARM and so on, is there a big performance difference there? I'm thinking especially about the number of registers, much lower in x86 and so on.
Yeah, so when it comes to register allocation, we don't have good numbers yet because we're not doing any of our own register allocation. We kind of trust the compiler to do a good job with register allocation at the micro-op level. I mean, we have a smaller number of addressable registers, but really the actual number of registers in the machine is much larger than that. So I'm actually not too worried about the number of registers. What concerns me more is actually just sort of the format of the relocations that we need to work with. On ARM, where we have these fixed size instructions that are 32 bits, splitting 64-bit loads is actually sort of a source of inefficiency. And so we might look into sort of more aggressive rewrites there when actually linking the code.
And the preliminary benchmarks that you showed, were they on x86 or ARM?
Yeah, so that's x86 Linux is usually the number that I go towards. On ARM, we actually aren't doing as well, so it's, I think, somewhere in the neighborhood of 5 to 10% slower still, and that's specifically what the people we're collaborating with at ARM are helping to work on.
Thank you.
Thanks.
Thank you. Thank you for a very good talk. So I have just a quick question. So you said memory overhead due to JIT compilation is pretty limited, but is that does it include VM the size of the VM itself, or just runtime memory for the code?
So that 10%, or now the 6% number that I quoted of the memory overhead is the entire resident set size of the interpreter as it's running the benchmark, so the high water mark. So basically that includes everything, including the JIT code. So we can say that the JIT code and all of its templates that we've compiled correspond to a 6% increase in runtime execution size.
That's very interesting, because most of the VM, including a supporting JIT compilation, takes 10 times or 20% or more than that, 50% overhead for the memory footprint of the VM. So that's why I wonder why the system is so small.
Yeah, I think a big part of that is because we don't have a lot of de-optimization information on side exits, and once we have performed our optimizations on the linear traces, we throw them away. So for things that are doing like these de-op tables and reconstructing frames and keeping all of this metadata around, I think that's probably a huge source of overhead for more aggressively optimizing JITs. And so we may find ourselves actually having more memory overhead in the future once we start doing that. But basically right now, the increased memory overhead is purely just binary code.
Thank you.
Just as a random guess, maybe after the stack, most of the memory operations are now on ref counts.
Yes.
So do you have any optimizations to try to fuse increase, decrease reference counts on sections of code that happen to be ref count neutral, for example, swapping two variables?
Yes, yeah, so when we do our abstract interpretation, that actually gives us a nice building block for doing like alias analysis, where we know that there's a strong reference in like a local variable, so that when we push it to the stack, as long as the stack reference outlives the local reference, we don't need to actually ref count it. Deferring ref counts is something we're looking into, and that actually overlaps with a lot of the free threading work that Meta is doing, is because for obvious reasons they want to reduce ref counting on hot objects as well. And so we're all interested in different ways of actually reducing the number of reference counts, whether that's with the intent of reducing contention or with the intent of actually reducing the work itself.
Thank you.
Thanks, great work. So you've done all this sort of building a foundation for the future, and it's sort of performance neutral at the moment, so the overhead is kind of paid for. Do you have a sense of how much performance you think you can get over the next 1, 2, 3, 4 years?
Yeah, so like, again, this kind of comes back to the benchmarks. Like whenever you say, oh, we're gonna be this much faster, you have to say like, okay, according to what, right? So I can show you micro benchmarks that are gonna get instantly fast, basically, but what we're really interested in is our full benchmark suite. So to kind of give you an idea, that benchmark suite, for better or for worse, it represents real Python code, and it actually spends only about 1/3 of its time in the bytecode interpreter. So hypothetically, if we were to make the interpreter infinitely fast, we would see a 33% improvement, right? I think that when people talk about making Python faster, though, they're talking about pure Python code. And so we don't really have a great idea right now what sort of performance improvements we can expect. We can look to projects like PyPy or any of the JavaScript JITs to sort of see like what that kind of upper limit is. I would expect that probably our ceiling would be closer to half or 1/3 of the speedups that they're experiencing, just because we have a lot less resources to pour into making like a 6-tier super optimizing JIT, right? Yeah.
What's this XKDC CD?
I don't know. Look it up.
And I have a question about your future work, the object model and garbage collection. Python has a bunch of libraries written in native code like C. So does they affect the native code? Does the object model change on object model and garbage collection affect native code?
Absolutely, yes. And so that's kind of a big difficulty in actually changing the way that like objects themselves are laid out, is because you have kind of both API and even ABI stability guarantees. So at the API level, we could say, okay, everywhere you're using a PyObject star pointer, you use this opaque handle instead, and you need to pass that to all of these library functions and don't actually access anything yourself. ABI stability is a lot more complicated because we have what's called the stable ABI, which basically says that if you compile on, say, 3.7, it'll continue working into the future without needing to recompile your extensions. And there's a lot of code out there that actually uses this. Similarly, it's really tough to play with these changes because it breaks, like our benchmarks sort of act like a canary here, where if we make a small change and a bunch of our benchmarks just start crashing, we're like, oh, this might be actually a disruptive change. So for example, to reduce the overhead of ref counting, the incref and decref macros that C extensions use are actually C macros. So those aren't something where we can actually just like swap out the implementation in the interpreter that they link against. That extension actually needs to be recompiled if we change the way ref counting works, for instance. Same with the garbage collection protocol. There's like a very clear contract of like what interfaces you need to implement and what sort of information you need to give the garbage collector, and even things like the size of the GC header on objects are things that people are implicitly relying on, whether through the ABI itself or just because they're doing weird stuff with like pre-headers and stuff. So yes, it's very, very tricky.
Thank you.
I think that the ecosystem of C extensions is a huge source of Python success, but also a huge source of frustration for those trying to make it faster.
So I want to ask a quick question. You mentioned that the relationship with JavaScript GC or JITs, and I've had the pleasure and the pain of working on industrial teams with these. And I was kind of curious if you could expand on how you see the relationship between the two. Are there unique challenges in the Python space, or is your focus more on building like developer effort efficiency? Like what's kind of like, can you just take everything that they do in JavaScript wholesale, or what's like, where's the unique challenges with Python?
Yeah, I'd say the unique challenges are both sort of at the language level and at like the, or I would say like the ecosystem level, and also just sort of like the maintenance burden itself. So we don't have a ton of resources to basically throw behind building and maintaining these huge optimizing JIT compilers, especially when we have basically a volunteer workforce of people who maybe aren't experts in JIT compilation, right? And just want to add a new language feature that people are asking for. For reference, this copy and patch implementation, people are already proposing new language features like tagged template strings and things like that. And it was kind of cool. A bunch of us were getting together at a core developer sprint, and the JIT was just automatically able to handle all their new bytecodes with no changes. And same with like being able to fix bugs, especially serious ones. Being able to make a change that fixes the bug in the base interpreter and also have the JIT and the optimizer be updated as well, it can't really be undersold for a project like ours. In terms of the ecosystem itself, we have kind of the problem of third-party C extensions, the blessing and the problem, right? Where it's like we have all these gobs of code that has been written using our ABI or has been compiled using a BI that they expect to be stable. And so that's kind of a unique challenge for us because it really, really limits what we're able to do, especially since implementation details like ref counting and the layout of objects was leaked so early on. And then there's other things too, like for example, the free threading project is a really exciting new change to Python, but it also introduces challenges that JavaScript doesn't have because JavaScript is a single-threaded execution model like Python was for a very long time. And so I think it's kind of a combination of like language level problems, ecosystem problems, and when I say problems, I mean challenges, right? And like the actual resources that we have as a project. But like where we can look to things like JavaScript is just when kind of looking into research for just optimizing dynamic languages, there's a lot of really good stuff there. I also think it's great to look to PyPy as well because they have a lot of the same problems we have. And I think that a lot of this sort of ecosystem stuff has been part of why PyPy hasn't been so widely adopted, even though it's a great optimizing JIT compiler and built on a really cool framework. And so I think that kind of gives us an idea of like what's worth trying and what's not worth trying necessarily.
Let me bogart one quick one now. Any security concerns about adding a JIT?
Always, yeah. If you ever want to file a CVE against CPython, it's never been easier. So I don't know if there's any security researchers. Yeah.
So you mentioned both lifting guards and like removing them opportunistically. How do you ever do that if like a user can arbitrarily jump into your for loop and you've lifted your guards out and they've set local variables and those guards are no longer safe?
Yeah, so we do have instructions that are inserted after escaping operations. So any code that could basically go somewhere that we don't manage as part of our actual trace, we basically perform a quick check on a flag after every single one of those calls has returned. So that could be something as kind of annoying as decoroughing a reference, since that could have a finalizer, or something as routine as just calling out to a C extension that we don't control. So basically, if they invalidate the world, we just have a quick bit that we check that will basically just exit the JITted code and sort of fall back on the interpreter. And so that's sort of how we maintain our sanity, is by assuming the world hasn't changed all over the place and making it very, very fast to check when it has.
Yeah, I agree that developing a new modern benchmarking is significant. I suppose that nowadays most runtime time is spent in a library like a NumPy. So I wonder, how much impact you expect by JIT compilation of pure Python code, because it's Python code is used as a kind of scripting language nowadays. So, well, in a worst case scenario is that, even if you develop a nice JIT compiler, the total execution time might not very much change.
Right.
What do you think about that?
Well, I mean, our goal is pretty clear. Our goal is to optimize the single-threaded execution of pure Python programs. So whether that affects you significantly will depend if you're spending 90% of your time in a NumPy, operations, or in code that's JITted by Numba or TensorFlow or whatever else. So like, what we can do is we can kind of smooth out the edges. So if we can make it easier to call to and from NumPy, for example, by basically providing easier API boundaries, or by allowing them to, for example, register specializations when they're loaded or things like that, then it becomes a little easier. And kind of our hope is that moving away from heavy things like NumPy, our hope is not to move away from heavy things like NumPy, but like shifting the conversation away from heavy things like NumPy. One thing that we've observed is it's actually frustrating to sort of project our traces when there's just gobs of C code in between that just kind of break up our traces. And so what we feel like we're moving towards is where previously a lot of code, like small utility functions, would be moved out of Python and into C for performance. We're already starting to see that that may be a kind of less of an attractive option, which kind of shows that we're on the right track. There was at least 1 or 2 projects that had some accelerators in C that they found were actually a lot more performant once we landed the specializing interpreter, just to leave in Python code. And for simple utilities like, for example, the any and all functions, min, max, a lot of these built-ins that are implemented in C might benefit from having pure Python implementations that we could inline more aggressively.
Thank you.
Okay, so that concludes the keynote. VMIL will start up again at 2 p.m. with the language implementation section. So now there's about 25 minutes until lunch.
the sound. If the microphone stays there,
and it is entitled Smarter Contract Updates with Orthogonal Persistence.
Thank you very much, Ben, for the introduction. So as Ben already revealed, so it will be about blockchains, and I will mostly focus from like the high level of blockchain, how to use it for programming, what does it mean to implement programming languages on it. So we can consider blockchain as a virtual machine, a new taste of a virtual machine that serves for distributed computing in a secure way where you have untrusted nodes. And here we can, like the more powerful blockchains, allow to run programs in a very like advanced way. It can be programs written in high-level languages like Solidity, which is an Ethereum language, but also Rust, JavaScript, and various other languages are supported. So it's really general-purpose computing. But at the same time, it's also a storage system in the sense that blockchain is used to store the state of the programs or parts of the state of the programs in a secure distributed way. There are various application cases, smart contracts, which the title says, but it goes far beyond. It can be any application. It's obviously it makes most sense where there's decentralized cases on untrusted basis. So I focus here on a very specific topic, namely the changes of blockchain programs. So once people have a blockchain program, they deploy it. It can be a smart contract or something more complicated. But then after some time, it's nearly always the case, there's need to change the program, be it because there are bugs, a feature extension, and other reasons. And then, like there, as usual in software development, there are two aspects to consider. One is changing the program logic, but also to retain the data, to migrate the data to the new program version. How does that look like? Nowadays, this is like not so easy, at least on a blockchain world. Still, it also poses in traditional software engineering. There's also it's also sometimes quite involved. So if we look, for example, at the most prominent compute blockchain, Ethereum, it's a very simple model. So whenever a program, a smart contract has been deployed, it's non-alterable. It stays there forever. And then still people in practice need to be able to evolve the program. That's why they need to think ahead and design a so-called software architecture that is designed for switching the implementation later on. So what people do is designing a redirection system where they have like multiple smart contract components, designing a full application, and then they prepare changing the implementation by, in fact, having something like a pointer to another smart contract that is the implementation. So the downside here is extra programming work. Also, the data often lives in this proxy, like this first smart contracts for security reasons, but that also means that changing the data is very, very intricate. One can only map the data to a new form, but it's very limited. Also, I believe there's like a security risk involved there because the actual implementation depends on the value, like this redirection value, and that may be easily changed without that people may notice so transparently in the community. So whenever you use such an application, one needs to be very sure what's actually the binding behind. It may happen that at some later point, controllers of the smart contracts may then change it to another implementation with some logic that was not anticipated. So that's why more advanced blockchains have a dedicated upgrade mechanism so that it's more transparent, that people can even vote and review what's the new code to be installed, and if a majority decides this is safe to evolve, then that upgrade happens. So there's an institutionalized mechanism in the blockchain. But however, that's interesting to see when it comes to how from the implementation perspective, from the memory perspective, how is that the persistence implemented in those systems? There's still this reminiscent of traditional computing. So typically these blockchain programming languages and also blockchain implementations, they have several kinds of memories. One is the domain memory that's very similar to the RAM or like the classical programming language, where you have like a volatile memory that is just there for a certain time of the program, And at latest, when the upgrade happens, this temporary memory is typically erased and is gone. So that's why people, when they design blockchain programs, then have to think about the further longevity of the data. So similar to database management systems. So then there's like a secondary storage typical to disk, and if the blockchain is quite, let's say, used at a low level, then people even have to work on that secondary storage that's explicit memory accesses and then comes with all the problems, safety, that this is secondary memory is not managed. You may like, have misinterpreted data or data corruption. And it's also quite expensive because the data needs to be constantly copied and serialized back and forth between these two memories, because the only memory to work on the data is typically the main memory. So this is a burden. That's why people then design wrappers on top of that, like frameworks or library, which ease that use of that secondary memory, that persistent memory. And this is just an example, but this then also comes with downside, like it's boilerplates. It's in the end very similar to these object database mappers with all the aspects, and it's also performance-wise disadvantage because there's always serialization overheads. And we will actually thinking of how, at least with blockchain, one has like a new kind of a virtual machine and also maybe a little bit of different approach of software engineering, how one could ease that in a very, very fundamental way. The most ideal one would be that the blockchain, the memory is anyways persistent. And if we could exploit that and have like the program being like living conceptually forever, but however enabling changes to the program so that the state of the program is automatically persisted, and the programmers can just use the main programming language, the core language concepts, like can design any graph style, object-oriented structures without needing to think about that. And this is then automatically, so to speak, the native program state is also your database in that sense. And so there's no like extra databases or secondary memories or special APIs involved, and this, especially in the blockchain programming world, makes sense because any programming complexity may be a security risk in that sense. If there are bugs, usually there's financial, like monetary values stored, and so this is like people tend to have like small size, or let's say like reduced complexity as much as possible. So that's what's known in literature as orthogonal persistence, so that the program state is naturally persistent, and we try to implement that and top it off with some extra aspects that we want to allow simple or also custom data migration to allow any kinds of program changes. And it's very important that the runtime system ensures data consistency such that people cannot mess up, like corrupt their data or misinterpret data. And we also aim for like good performance in that sense that we have very fast upgrades and also data accesses become very, very efficient. So I'm working at a foundation, as Ben mentioned, the Definitive Foundation, which is somehow the main contributor to this internet computer blockchain. That's a powerful compute blockchain that uses WebAssembly as the intermediate representation on that virtual machine that I mentioned, and it has like one of these dedicated upgrade mechanisms. And for that blockchain, there are various programming languages supported, but however, there's one bespoke programming language, Motoko, that is designed to optimally support the concepts of the internet computer. So it compiles to WebAssembly. As flavor of the language is a little bit a mixture of C#, TypeScript, or Camel, so imperative, object-oriented, and functional. And very importantly, it's a memory-safe language that is garbage collected, so trying to avoid as many bugs or many hassles for programmers as possible when it comes to memory management. So just to give a little bit of a peek how the an example, a very simple example in Motoko looks like. The basic components of the program are actors that can be deployed on the blockchain. And the actors are stateful in that sense that they can have like variables here. That's the top level variables of the program. Here it's a very simple example of a log system, a message log system. So we may here declare a messages variable that is nothing else than a list of text messages with some functions to populate it and to retrieve it. A little bit like maybe the only artifact of persistence is this stable keyword, which means that this variable and also its transitive state is retained like forever or even across upgrades. So now we have this simple program, and then we want to evolve it, and we may add some functionality, maybe add some state, and later on we'll see we can also manipulate the data representation. And now I extend the program, deploy that new version, and then people can actually vote on whether they want to accept that, or if not, then that this change will not be applied. So what happens here, we have like an extended version, but however, there's like a specific semantics in how the state gets, like on an upgrade, gets retained. So whenever a stable variable has already been declared in the previous program version, the system checks whether it's compatible to the new version, some changes can be done, then this is just retained, and in this case, the initializer is not executed, so it's like that code in this new version. However, we have a second variable declaration that it was not there in the previous version. That means that the initializer will be executed. The initializer can reference other state that is around. Here, for example, the message object are shared by references, and then we can add functionality or replace functionality. So a little bit specific here, the programming language has two keywords for top-level variables. One is stable, which is like the most commonly used, and we plan to make it the default kind of modifier in the future. But there's like some, for backwards compatibility, some aspects to be considered there. And everything that is transitively reachable, directly or indirectly referenced from stable variables is considered persistent, and this is the state that needs to survive the upgrades. However, in certain cases, one may have like transient state that is maybe statistics that can be safely reset on an upgrade, and this can be declared flexible, and flexible means these are all the non-persistent objects that are solely reachable by flexible variables. These are retained just during the same version of a program. And of course, because of manipulation of references, and so they may garbage arise, and that's where the task of the garbage collector comes into play to collect the garbage objects. So I mentioned that the stable keyword is still an explicit keyword. There's a little bit of challenge. We cannot support all types for like long-term persistence, and it is due to the nature of functional paradigm of language. So whenever we have lambdas or promises, futures, this is something that is inherently transient, and it's very hard to map it to a new program version. Like actually local named function reference, that's something that's doable. I'm quite currently working on that. But somehow we have to restrict the type system in a way that not everything can be retained across upgrade, and we want to make it static. So this compiler checks whenever like this stable variable, that everything that is reachable from that, the static like fixture of types that can be reached from that is like fulfilling this condition. So that's the reason why we have that. And then when people want to make changes, the compiler and the runtime system supports what I call implicit migration. So there's no automatic handling on the upgrade, so nothing needs to be done by the programmers. These are kind of simple evolutions that can be done and that are safe from a memory mapping perspective. This is things like promoting types to supertypes, for example, adding and dropping actor fields, and so on. And anything that is more complex is then task of the programmers to implement that, like by custom migration, because there can be any kind of evolution that may be needed for a program. Just wanted to showcase like an example of a little bit of a more complex migration. This is actually like a refactoring migration. I've now introduced like these two variables, but however, maybe I want to group them to something like a logs list that is like pairs of text messages and the time when they were allocated. And this can be done in the language by two steps, like actually two upgrades in the sense. Like what we need to do is first do like an intermediate version where we keep the old declarations, because that's what's like retained by the implicit migration. Then we have access to the old state, but then may introduce new variable declarations with our desired like new type. And then we can provide with the initializer or specific additional functions, we can then add the copying mechanism, or like the logic that migrates that to the new variable. And then if we are happy, we can then at a later stage, this can also be part of the next like semantic upgrade, we can then safely drop the old variables. So the language somehow is prepared to also do complex migrations. That's how we do that. And the runtime system always checks whether any of those upgrades is compatible, like in the sense that it only has implicit migrations when it comes to the systems level. So in order to implement that, we had to do some changes, like in a sense, like the full stack, like the blockchain, but also compiler, the runtime system. First thing that is like specific to our blockchain, we had to somehow enable that the main memory, it was already persisted in the blockchain, but however just artificially erased on upgrade, just because classical mainstream programming languages cannot cope with retaining the main memory. So we had to somehow switch that off for Motoko programming language. And then also for historic reasons, we used VMIL memory 64 when it came to secondary memory, but not for the main memory. So that's because people just had like more temporary data stored in the main memory, then there was no need in having like a large scale main memory. But however, if we want to have like full power for the sense of orthogonal persistence, and we want to focus on the main memory for the implementation, we also want to have like the same capacity for the main memory. That's why we turned on memory 64, which is a WebAssembly proposal in a very far stage. And then an important thing is, why do classical like language implementation are not like by the off-the-shelf suited for this use case? That's because the compiler arbitrarily rearranges the allocations when it comes to static objects or so in the programs with every, let's say, change of a program, and that's something that we cannot use. So we have to have a design where a new program version is able to pick up the existing memory state that was left behind by the previous version. So for this reason, we designed what we call a stable heap, or like a heap design that is persistent, and where the compiler cannot make any whatever specific adjustments to where things are allocated. So what we have is some metadata that is like the anchor point, the root point, where every new program version, even if we change our runtime system, needs to start and see what's around in the main memory. And for example, a garbage collection state where there are root pointers in the dynamic heap, and then everything needs to be placed in the dynamic heap. So we had to get rid of all what many compilers do static allocations, but only use dynamic allocations. And whenever there's something that used to be static, we do that by having a root pointer in our metadata. So a nice feature actually from WebAssembly was that we are also able to load data segments. So it's, for example, for literals in the programs, or like some static data that we do not need to denote a specific location in the main memory, but just keep that open, and then we can lazy load that at runtime to a dynamic address. And then everything else is on the heap. If we have like compile time known objects, something like static objects, we solve that by having a pool of such objects in the heap where we can look it up. So one extra indirection is needed, but that's the extra price of that. Also, we have a incremental garbage collector because these can be quite large programs, can support up to 400 gigabytes like of memory per component in that blockchain. So a classical stop the world garbage collector is not working, even if we have a few gigabytes or so. This is also because the blockchain imposes a certain transaction limit, like one cannot have like arbitrarily long functions being executed, but they need to stop at some point. And then we piggyback the garbage collector on those function calls. And here with the upgrades, we actually want to have the upgrades very responsive. We don't want to wait until the garbage collector has fulfilled its whole round of increments until it's reached like a stage where it has completed its work. But however, we also want to perform an upgrade while the garbage collector is on work. That's why we also designed the garbage collector state to be also persistent, and this proves to be very easy because we place the garbage collector state also in that metadata that can resume from that. And as mentioned before, like we have two kinds of roots. One are these stable variables, and the transient variables are also root pointers for the garbage collector, and some other stuff, continuations. So very importantly, we want to have a stringent check when people like install a new version, that the new version is somehow compatible to the state that is around in the memory, because object may be layout differently. That's why we support certain implicit evolutions that can be safely resumed from memory without having to change the objects. In the end, that's our motivation of defining these implicit data evolutions. And we enforce the compatibility by storing the types, the fixture of all types in the program into a very efficient way in a kind of a type table, and we check the type table that is existent from the previous state that is stored in the persistent heap with the new desired type table of the new program version. And if there's anything that does not fulfill our implicit evolutions, we reject the upgrade and roll it back so that it's like as if the upgrade was never happened. So this is just to ensure that these upgrades from the memory memory perspective stays consistent at all times. We used it at a type level and not scanning the heap again for like scalability purposes. We want to support very large heaps, so that's why here it just depends on the number of types, which is constant to the heap size, and that's why we enable very fast upgrades. So there's nearly nothing to be checked except this type table. So I did some excerpts of measurements, like now for this new orthogonal persistence for Motoko, that's the blue line, with this very cheap constant time memory compatibility check that just comes with a few thousands of instructions, 10,000 of instructions, just comparing it to an old mechanism that we used that was actually serializing all these objects that are reachable from persistent variables to the secondary memory. And yeah, apparently as expected, the serialization is something that depends on the heap size, and if this is just an excerpt for one example program, and here we clearly see that this is really like performing constantly. Why does this matter? Because as mentioned before, there's a transaction limit on the instruction. So assuming people have now a very large heap, they would suddenly run at the limit of the instruction, and then it could, with the old mechanisms, could no longer upgrade because there's too much to be moved around during an upgrade. I was also interested to see how does that affect on performance, like when there's no upgrade, just an ordinary performance of the program, because now we can just work with the main memory. There's like no overhead involved in using the secondary memory. And also, and that's the biggest gain, programmers can now design any arbitrarily shaped data structures. They're no longer confined to a specific library where typically there is only a specific set of data structures that's around. Maybe it's a little bit unfair comparison, but I now had the challenge to compare Motoko with another internet computer implementation. I compared it against Rust, which also many people use. And in Rust, there's a library for enabling data persistence that's called stable data structures. And however, the library just has a specific set of data structures, like there's a key value store, like a B tree, there's some stable vector, like a stable list, and so on. And this is just exert in that sense, but it shows the only artifact that's mentioned for Motoko is still that stable keyword. Maybe you can get rid of that in the future. And there's way more boilerplate involved, and it becomes more complicated if you really have to map the data to squeeze it into specific data structures that are around. And then I was trying to implement it as optimal as possible in both languages, and then measured what's the time of the accesses of reading out or retrieving elements in both systems. Here the difference is on logarithmic scale, and it's measured what we can. We have a synthetic performance measure on the blockchains because we cannot use wall time or so. It's something that needs to be deterministic. And what's measured here is the number of WebAssembly instructions. Some instructions are more cost weight, so it's weighted costs per instructions. And here it's really a dramatic difference. It's a logarithmic scale, and this is due to mostly modeling reasons. So in Motoko, you can just model cases. For example, if you have a queue, you can model it as a doubly linked list, but however, doubly linked list is not available in these stable data structures, then one needs to somehow map that maybe to a key value store, and the index denotes the position in the queue, something like that. That's why there's what I meant, it's a difficult comparison. You have different possibilities in modeling it. Also here, to navigate from object to object, of the domain model, it's very easy. You can just dereference, and in the other world, you have to access have to introduce an index in these stable data structures, retrieve it, copy it to the main memory, and that's why the difference is so high. To conclude, so we had this aim to make smart contract upgrades easier in the way that it's simpler to use, but also safer because the runtime system guards it, less code, and it's also cheaper in the sense it costs less because the instructions is what you pay, the performance is what you eventually have to pay for. And we've done that with orthogonal persistence by pursuing orthogonal persistence to allow people to model data of any shape, have full liberty of how they want to design and use their data, supporting implicit and any more complex data migration by explicit custom logic in a well-guarded way with these compatibility checks that check that at least at memory level, there's no data corruption or misinterpretation, with very fast upgrades, constant time upgrades, and also very nice performance improvements when it comes to just running the program as a whole. Thank you for your attention.
Do the actors run concurrently? Do the actors run truly concurrently?
I did not understand. The upgrades to?
The actors run concurrently?
The actors run concurrently. Sorry.
How do you deal with the race condition?
Say again?
How do you deal with the race condition from the persistent data? How do you deal with the race condition?
So there's no race condition. There are race conditions, but data races inside an actor are are not possible. But of course, you can design, because there's also an asynchronous programming model, and as everybody knows, in JavaScript, so any await point is potential for unconsidered interleaving. So it's not like addressing like race conditions in that sense, but however, importantly to say here, the memory management, which I explained before, is actually per actor. So every actor can actually have their own whatever persistence mechanism. So we may have like a ensemble of Rust implemented actors working together with these Motoko actors, and that's how we can combine, let's say, managed with less or like differently managed Rust. For example, Canis is combining orthogonal persistence with classical persistence approaches.
Thank you.
Welcome.
Hi. Great talk.
Thank you.
In your example, I didn't see initializers when you were converting from events to times. Maybe I just missed that, so I didn't understand how you made that transition.
The very first?
I assume it's by running initializers. Yes.
Yeah. Here the initializer is a little bit hidden, but this is like what's the list map here. So I take the messages, like walk through the messages, and then it's very primitive. I just assign time 0.
So then, in the multi-step conversion, you could have added another step, which was to convert logs back to messages, just copying it over, and then the whole thing ended up just being a redefinition of messages.
So you mean here that I reintroduced?
Another step that says messages equals logs, and then another step that deletes logs, right?
Yeah, that's
and
possible.
So if I had just, it seems to me like you could automate this whole process just by saying, hey, I'm changing messages to this new definition. Here's the conversion function. Generate all these steps.
I completely agree. Like that's actually also something that we have in mind, because these 2 upgrades is still like an extra burden or so, and this is actually very easily to be done, that we can somehow define, let's say, more flexible migration to any new state. We are thinking of something like having a mapper function where one can access the old state but doesn't have to materialize it as new variables or so, and that would then ease these steps. Then you can just
some kind of annotation you could throw in.
We thought about like providing a migration function or so that just applies if there's a previous state, maybe even multiple, that you can support multiple, like migrations from multiple previous versions depending on what was around on the blockchain before. That's a good hint, yeah.
All right, let's thank Luke again.
Thank you very much.
So our next speaker is a disembodied video. It will be synthesizing efficient superinstruction sets for Ethereum virtual machine.
Hello everyone, my name is Xiaowen Hu from the University of Sydney, and this is a pre-recording of me presenting our work Synthesizing Efficient Super Instruction Sets for Ethereum Virtual Machine. This is a joint work with my colleagues David Zhao and Bernhard Schultz. So what are super instructions? A super instruction is a sequence of multiple individual instructions combined into a single, more complex instructions. It is a very common optimization technique used in interpreter and virtual machine optimization. For example, instead of executing load, add, store separately, we can combine them into a single super instructions called load, add, store. This reduces the overhead of dispatching each instruction individually. So why are we interested? Well, usually few instructions in the interpreter's runtime lead to few dispatches, which is a crucial component in the interpreter's performance. Secondly, super instruction can take advantage of the additional context, which allowed for more optimization. For example, if we're going to apply super instruction on a stack-based virtual machine, then the usual stack-related operation within the same super instruction can be removed, such as push and pop. In this work, we use dispatch reduction as the metric for the super instruction evaluation, which we call GAN. Historically, many super instruction implementations have relied on manual selection. This approach can be inefficient, especially for complex applications. Automatic selection, however, is NP-hard. While previous approach provide historical-based strategy and offer a simple yet effective solutions, they often ignore overlaps between super instructions. We will talk more about overlaps in the next slide. So our research here aims to address this problem by providing maybe just a new perspective on automatic super instruction selection. So what is overlap? Consider this example. If the super instruction add load is already selected in our super instruction set, should we consider adding add load start into our instruction set? On the one hand, the existence of add load reduces the benefit, in other words, the reduction in dispatch of choosing add load start. On the other hand, using add load start may reduce the places where we can apply add load. Simple rank-based selection does not consider overlap. They evaluate the gain of all potential super instructions only once and then select them based on their ranking. Other strategy may re-evaluate the entire problem at each new iterations, which make them non-incremental and sometimes inefficient. Some approaches also reduce the problem space by limiting the size of potential candidates. For example, they only consider super instruction whose size does not exceed 4. Our solution combines offline dictionary-based compression techniques with greedy heuristics, allowing us to handle overlap incrementally. This approach strikes a balance between selecting effective super instruction and managing overlap, providing a new perspective for this problem. Before moving on, let's talk about Ethereum Virtual Machine, which is the target platform of our work. The EVM is a virtual machine for executing smart contracts on the Ethereum blockchain. And the EVM takes input a sequence of EVM bytecode. The bytecode representation of those smart contracts are then stored on the blockchain. This allows people to replay those smart contracts anytime, anywhere they want. And it creates a large data set for us to train and generate super instruction, which is very useful for our use case. Next, let's talk about the recursive pair algorithm, which is the offline dictionary compression algorithm we chose in our work. The recursive pair algorithm is a compression technique that identifies and replaces the most frequent pairs of symbols with new non-terminal symbols in the dictionary. It does this iteratively, reducing the sequence lines by 1 at each step until the input text only has 1 symbol left. This results in a dictionary of new symbols that map back to those original pairs, creating a more compact representation of the original data. Now let's consider an example. At the beginning, the pair SH and SE both appear 3 times. When a tie exists, we just choose arbitrarily. So here we choose SH for the replacement, and then replace it with the dictionary symbol 1. At the next iteration, SE becomes the next candidate for replacement because it has the highest frequency, and it is replaced with dictionary symbol 2. At the third iteration, just to remind you that at each iteration, the recursive pair algorithm updates the frequency of all the symbols. So at the last iteration, the sequence space dictionary symbol 2 becomes the next candidate for replacement, and is replaced with a new symbol. The result of a recursive pair is actually a context-free grammar, where each production rule is of the form V to alpha beta, where V is a non-terminal symbol from the dictionary, and alpha beta can be either a non-terminal from the dictionary or the original symbol in the input text. So on the left-hand side, you can see the derived rules, and on the right-hand side, you can see the grammar tree, which also happens to be a binary tree because of the nature of a recursive pair. Now let's have a look at our systems overview. We start by tracing and recording runtime information of smart contracts executed on the blockchain. In particular, we are interested in basic block execution frequency, as it is the important factor in our super instruction evaluation matrix. Next, we apply the recursive pair algorithm on those basic blocks, which effectively results in a context-free grammar. In our case, a binary tree. Each node on the tree represents a super instruction candidate. We then choose a certain number of super instructions on that tree based on our greedy heuristics, and we generate them into a new Ethereum virtual machine with the capability of executing those super instructions. So to trace basic block, the EVM code is instrument to enable the tracer to record a list of executed operations until a branching operation or an exception is encountered. So for branching operations, we're referring operation like jump, jump I, or any operation that causing early termination. The reason for that is our super instruction does not cross basic block boundary, so there's no point of recording frequency across span basic block. So up on encountering a branch, the tracer will store the recorded instruction into the database with an ID and frequency count. So the IDs can be used to uniquely identify a basic block sequence. Next, we use recursive pair to analyze the profiling data we just obtained from the EVM tracer. We use a modified version of recursive pair algorithm for analyzing basic block sequence. The input of our recursive pair algorithm is a concatenation of the basic block text representation separated by a unique marker sigma we manually added. And our recursive pair algorithm will never choose a pair that spans across a sigma boundary. This is to ensure that our super instruction does not span across basic blocks. Of course, there are super instruction variants that support crossing a basic block boundary. However, in this work, we mainly focus on classic super instructions. And each basic block is associated with a frequency count FB, which is also sourced from the EVM tracer. Next, we move on to our greedy selection. At initial state, our greedy selection simply calculates the dispatch reduction of all super instructions given by the recursive pair algorithm, with using the length of the super instruction multiplied by their frequency. In other words, each node in the context-free grammar or in the binary tree given by the recursive pair algorithm is associated with a estimated gain. And at each iteration, the super instruction with the highest estimated gain is selected. However, at each iteration, after selecting a super instruction, the gain for the remaining super instruction in the binary tree will be updated with our algorithm. The update can be mainly split into two parts, the frequency update and the height update. For the frequency update, we start with the select node V using a BFS. For each child node C of V, we update its frequency. So the frequency of C, the new frequency of C, will become the old frequency of C minus the frequency of V. And this update propagation will stop when we reach an already selected node. The rationale behind this update is that selecting a sequence like add load star reduces the frequency of its subsequence, such as add load, by the frequency of longer sequence. In another word, once we already select add load start, there will be less places where we can apply add load. Therefore, the frequency update reflects this decrease in frequency in the potential application of the subsequence. Here, the figures demonstrate the idea of frequency update. Each node is associated with a frequency. Assuming A is selected, then we will update the frequency on its children B and C. Originally, B has a frequency of 80 and C has a frequency of 100. Because of A is selected, the places we can apply for B reduce by exactly the frequency of A. So the new frequency of B becomes 40, and similarly, the new frequency of C becomes 20. Figure B demonstrates one propagation stop at a selected node, because the selected node already made our decision in our super instruction set selection. So once we reach a selected node, our update propagation stop. Next is the height update. The height actually refers to the length of the super instructions. They are initialized very straightforwardly. For any node, the height of the super instruction it represents is simply the height and the combined height of its two children. And this can be recursively calculated. And the update process is performed in reverse, starting from the select node V using BFS. For each parent P, we update P's height using the new P height becomes the old P's height minus the height of V plus 1. This process similarly stops when an already selected node is encountered. The rationale behind the height update is that selecting a super instruction such as add load reduces the potential saving of larger super instruction like add load start if the add load start has not been selected yet. This is because some of the dispatch saving from the add load start is now already accounted by add load. This is a figure demonstrating the height update propagation. Assuming we select a node B with a height of 4, we now need to update the height of A from 5 to 2. This is because A can now be represented by only two symbols, X and B, which is already a selected super instruction. Now let's talk about synthesizing those super instructions to be used by the Nicino virtual machine. The overall idea is to directly synthesizing Golang code to generate a jump table. This jump table can then be plugged in with the Nicino virtual machine during the project compile time and to be used later. The basic idea of super instruction synthesizing is to concatenate multiple operation code and just maintain the original computation without any extra optimization. And each operation code is mapped to its corresponding instruction as defined in the Golang EVM implementation. So really it's just a miracle which concatenates all the text together to form a large super instruction. Of course, we can apply optimization. The static nature of the additional context the super instruction provides can be utilized to add more optimizations. In this talk, we're just going to present some very basic, very overview idea. For example, we can provide a program counter simplification strategy, which combined the program counter update into a single update if the operation code within the super instruction, they are not PC sensitive. So by PC sensitive, I mean some of the operation code will actually need a very precise program counter value in order to faithfully reproduce the program. Other operation code does not really need a precise program counter of, such as push or pop. Those operations doesn't need a program counter to be correct. And we can also have some EVM-specific optimization. For example, all the instructions EVM, the Ethereum virtual machine, they have a guess cost, such that EVM add a predicate which check the guess meets the condition before executing those operations. Some of those guess checks are actually static. That is, there's no runtime information needed. So we can actually aggregate or combine those guess checks for multiple operations in the super instruction. This also saves our computational resource. And to be aware, those optimization idea cannot be only to apply to EVM, and it can also be applied to other execution environments. The super instruction framework is targeting at. Finally, we need a way to pass super instruction during runtime. This is done by using a whole heuristic algorithm for identifying super instruction, telling us at which place of the input EVM bytecode can we apply a certain super instruction. Then we use dynamic programming to select super instruction for maximizing dispatch reduction for that particular program. This turns out to be a very standard scheduling problem that can be easily solved by DP. Finally, let's talk about experiments. First, our research questions. Can our proposed selection strategy outperform simple rank-based or pairwise methods? Secondly, is our approach robust and feasible? Finally, we want to know to what extent does this dispatch reduction as a metric leads to overall performance gain. And at the bottom is our evaluation platform. We first talk about our super instruction selection implementations. First is plan, which is our baseline. Next, we have dynamic gradient, which is our main approach presented in this work. The n at the end indicates the number of selected super instructions. Next, we have dynamic recursive pair n. This is to select super instruction directly from the result of recursive pair algorithm without using our update strategy. Next, we have top kn. This is to choose the most frequent patterns with length not longer than k, which is a simplified version of rank-based selection proposed in previous work. Finally, all those dynamic selection method has a static counterpart. The static counterpart differs from that it uses the static code rather than the basic block execution frequency as a matrix for evaluation. We first look at some profiling statistics from our recursive pair and tracing components of our system. On the left-hand side, you can see that the memory consumption of a recursive pair is about linear to the size of the database, and the runtime of a recursive pair for each million block range can be complete within just a few hundred seconds, so which is very acceptable. On the right-hand side, for each million block, the number of basic block we obtained from our profiling tool. The notice part is that as EVM continue to processing more blocks, the number of unique blocks in each million block range grows significantly. Here, we examine the dispatch reduction ratio for various strategies under different settings. For this table, we choose n equal to 200, k equal to 4. This means we choose 200 super instruction, and for the top algorithm, which use a rank-based strategy, we limited the size of the super instruction to 4. Note that this restriction is only applied to the top strategy, but not to the others. Also, for each million block in the dataset, the training is derived directly from that million blocks, and the saving in dispatch or the dispatch reduction ratio are calculated from the subsequent million blocks. This is to prevent overtraining. For example, if the dataset, the super instruction is obtained from 0 to 1 million block, and then the reduction ratio is calculated for blocks from using the smart contract from blocks 1 to 2 million. From both tables, we can see that the dynamic version of the selection outperforms its static counterpart. This suggests that block frequency is significant in estimating the benefit of selecting a particular superinstruction. Furthermore, we observe that both the recursive pair and greedy strategy significantly outperform the top strategy. This demonstrates that our strategy outperforms simple rank-based selection strategy. Finally, we can see the greedy implementation outperformed the recursive pair implementation. This demonstrates that our updated strategy for accounting overlap sequence in superinstruction selection is effective and actually deliver better superinstruction selection results. This is the same experiment with a different configuration where n equals to 2000, where we select 2000 superinstructions. Similarly, we can find that the dynamic greedy selection strategies outperform all the other selection. Next, we perform an end-to-end performance of some of the selection strategies. In particular, we're interested in dynamic greedy versus dynamic top. We find that dynamic greedy with n equal to 200 delivered the best speed up of 8.45%. However, with n equal to 2000, we find that dynamic greedy also achieving a very high dispatch reduction ratio of 4.19 on average actually resulted in a performance decrease, specifically in the 2 to 3 million block range. The reason for that we suspect is that because of the large code sets when n equal to 2000 leads to code cache misses, slowing down the overall execution. For example, with 2000 superinstruction, it occupied 7.4 megabytes in memory, exceeding the 1.3 megabytes L1 cache of the testing machine. In contrast, 200 superinstruction required only 746 kilobytes of memory, which fitting well within the cache. Finally, conclusion. In this work, we developed an automatic framework to address the superinstruction selection problem. The framework uses offline dictionary compression and manage overlaps through incremental update propagation. Our approach was tested with large-scale experiments on the Ethereum blockchain and achieved an average speedup of 8.45%. Thank you.
Let's thank the speaker. So they are on the Discord. Can you hear me on Discord? We should have time for one or two questions for them if we can confirm that they can hear us. Okay, any questions?
I don't know if maybe try to talk to the presenter.
Can you maybe say something?
He's muted though.
Jiawen, you're muted. Can you try to speak? Okay, if they can't hear us, then we'll get started with the next speaker. It's unfortunate that we can have a question. So the next speaker is, how do you say your name? Fritjof. And it's about the fusion intermediate representation.
Thank you. Where did the cable go?
Hello?
Looks fine for me, but there it is. It's even me there.
Just one moment.
Okay. Okay, and it's just 3 o'clock. It's good. Okay, thank you. Good afternoon. I would like to present you the Fusion intermediate representation, which is the intermediate representation for a new language called Fusion, which has the goal to be an IR that supports static analysis, in particular for safety-critical systems. And this is a work in progress presentation, so I will only have 15 minutes. I will go quickly through all of that, but I'll be around all through the conference, so you can talk to me more in detail. A quick overview of what I'm going to do with you here now is I will start with a very, very quick introduction into the Fusion language, then tell you what I mean by safety-critical aspects before I then dive into the Fusion tool chain, in particular talk a bit about what static analysis we do, and then give you more details on what our intermediate representation looks like and end up with the status of the current project. And I'm from Tokiwa Software, a small startup company in Germany, and this is joint work with Michael Lill, my colleague there. So starting with the Fusion language, a very, very quick intro with a small example here is the main idea behind Fusion is to build everything in the language on a single concept, and that's the concept of a Fusion feature. In the small sample code, you see everything that is purple is basically a Fusion feature or a reference to a feature. And a feature is basically a generalization of something like a class, a method, a function, what you have in other languages. And a very important aspect of features is that they may be nested. Fusion is statically typed, and it is polymorphic in several ways. It has tagged union types, it has parametric types, and it has an object-oriented style of inheritance with redefinition. And Fusion is a functional language. It is pure and uses effects, algebraic effects, to model non-functional as impure aspects. Like in this example where IO out is an effect used by this small hello world example. Now, coming to safety-critical systems, and I start with a picture of a typical safety-critical system, which is a surgical microscope for brain and eye surgery. And I know from my previous life that these kinds of systems are actually developed with languages like Java that run the rather complex software on these systems. So that's where I see the need for actually higher level languages for safety-critical applications. So what do safety-critical systems typically have in common? What requirements do they have? Typically, there are fairly strict formal guidelines for the certification of safety-critical software. And there are different guidelines, different standards for different application areas like avionics, industrial applications, automotive, medical, and so on. And what these guidelines typically prescribe is a very rigorous development, and in particular, a verification and validation process. So you need very strict documentation and traceability to ensure that the application actually performs correctly. And not always, but often, safety-critical systems also require to be deterministic. So there must be worst-case execution times for all the operations. For memory management, for example, that means that you only have the option to use either real-time GC or static memory management. And you cannot use, or you have a lot of restrictions in the use of probabilistic algorithms like hash tables, where you cannot easily bound the execution time. And the idea behind the fusion intermediate representation is to have an intermediate representation that makes it easier to develop tools that help with the development, particularly with the verification and validation process of safety-critical software. So let me show you what our tool chain, and in particular the static analysis tools there, look like. This is a complete overview over our tool chain. It starts pretty standard with a front end that takes Fusion source code and compiles them into Fusion module files. And that does standard things a compiler front end does, checks for local correctness, type correctness, and so on, but also verifies things like supply chain security, that any modules we depend on actually fulfill what they promise. Then the middle end takes a set of Fusion modules and compiles them into a Fusion intermediate representation, which represents a whole closed application. So the main thing the middle end does is so-called monomorphization. So it replaces all parametric types by actual runtime types. It does things like dead code removal and some smaller optimizations. Now, on top of the Fusion intermediate representation, we can run different analyzers, optimizers, and the purpose of these is to verify the correctness of the application, so to verify the absence of certain runtime errors, to maybe specialize the code for better performance, do things like escape analysis, that we can know where to place allocations, that we can have allocations statically on the stack, or automatic freeing of allocations, or as a fallback if everything else fails, to fall back to the garbage collector. And also have tools that help with instrumentation, with test generation for all the certification artifacts that we might need. And now the result of these different tools is again the Fusion IR, which is then the input for different backends. And this is the backends that we currently support, which is a Java virtual machine backend where bytecode is generated, or C source code, or we have an interpreter as well. So now let me tell you very quickly about the details what the Fusion IR looks like. Fusion IR is basically a set of runtime features. A runtime feature is a feature like I've presented you in the beginning, but equipped with actual runtime types for all the type parameters that the features might have. And a feature could be one of 6 kinds. It could be a routine, which actually can run code. It could be abstract. It could be a field, a variable. It could be a choice. A choice is basically our union type. It could be an intrinsic, or it could be native. And 2 of these feature types actually define a type that could be the type of a field, which is a routine, which defines a product type, or a choice, which defines a sum type. Then all but the choice type are callable. So a choice cannot be called because the instance of a choice is created by an assignment. But only routines actually contain code, contain bytecode that can be executed. And I will quickly show you what the code in our intermediate representation looks like. The intermediate representation basically is using a stack machine. And there's a very small set of commands. It's only about 10 commands the intermediate code supports. And the most important one is a call, so a call to a feature. Then there's assignment of a value to a field. and there are operations to tag values, which is wrapping a value into a choice type, so creating a tagged union type value. And the counterpart to that is a match, which takes a tagged union type value and switches over the different instances that this might have. And actually the match is the only control flow operation that we have in our intermediate code, very similar to the Smalltalk talk we heard this morning. We don't have any construct for loops. What we do for that is we use recursive calls and tail recursion optimization in the backends to manage, to model those. And then there are some more intermediate instructions that I don't explain here in detail. Now, since we have so few, so few instructions, the whole complexity that we to run actual arithmetic and things like that, the intermediate representation uses intrinsics, so specific features that the backend or the analyzer knows how to implement to realize more specific features. So all the arithmetic, floating point, integer arithmetic is done via intrinsics, but also anything that affects the runtime system, so internal things related to effects are all done with intrinsics. And what that means is that any tools that run on the intermediate representation, depending on what they actually analyze, they could just ignore certain intrinsics if maybe the details of some floating point operations do not matter for a particular tool. Those can be just treated as opaque values, while those that are important for a particular analysis need to be implemented by the tool. So I'm coming to the end, the status of the project. Fusion is, and the tool chain is still under development. The language specification reaches a more and more stable state. The base library is still a big construction site and work in progress. We have the current implementation has backends running on the JVM and a C backend using Clang then to generate code. And we have basic analysis tools available. We're starting this month as a partner in a larger European project called Green Code, where with about 25 European partners, many large industries, we're developing this further. And yeah, basically that is my presentation. You find all of our sources are available on GitHub, and you find lots of information on our website and on our social channels. If you have any questions, I will be happy to answer.
We have time for probably 2 questions.
So if you go back one slide, please. No, sorry, not that slide. One more. Where the intrinsics? Okay, so just a question about intrinsics. So the idea behind the IR is to statically model and for safety critical systems. Now, for each of the intrinsics that you're adding here, is this within the IR, and how are you going to model that? So for each intrinsic for a particular machine, do you expect the features for that intrinsic to actually be fed into the IR? How do you model that in terms of timing, in terms of what its effects are? Does it have to be fed in, or are you abstracting that away in some way?
I'm actually, maybe I'm cheating a little, because basically the set of intrinsics could be considered basically also as a set of intermediate commands that we have there, but we treat them so differently. We treat them just as features that are marked as intrinsics. And depending on what you are you're interested in, you might need to consider them or you might not in your tools. So definitely if you do a static analysis to maybe determine the worst case execution time of a certain operation, you need to consider all of them and know the runtime performance that the backends will actually then require for those. Yeah. Thank you.
Any other questions?
Thank you.
So our very last talk of the session is going to be by Mark Marin, and he's going to talk about an effectively Omega C language and runtime.
Yes. Oh, we got to do this. On that side, and now I get to play the game where I very carefully go over. Don't have mirroring on, and present. There we go. Okay. Well, thank you everybody for coming to the talk. So this is kind of a work in progress talk. This is kind of an idea that's been, I was at Microsoft Research for about a decade, pivoting to academia. The last couple of years, I've really been thinking about this question of how do we build highly reliable software? And initially I came at this from the view of software reliability is proving some assertion about your code. So I had a really fun opportunity to work with some folks in investment banking about proving arbitrary properties about compliance software that they were building to do reporting for the SEC and stuff like this. So, but there were other conversations I had that were really kind of funny about performance, and so I wanted to share some of these with you guys and my thinking on this. And this comes down to this issue of when I started thinking about performance and compilers, it was, I'm going to have a set of benchmarks like DeCapo or Spec or something. I'm going to run this. I'm going to have JIT warmup. I'm going to discard some outliers, and I'm going to compute a geometric mean. Or I'm going to set up a web service, run some load test on it, and make sure that my response time is less than 100 milliseconds on average. And this is great. This is table stakes, right? Obviously, if your software is just terribly slow, it's no good. But this only gets you so far. This gets you deployed, but then what happens is you see, well, in practice, maybe my software responds in 80 milliseconds on average, but sometimes it's 50 milliseconds and sometimes it's 10 seconds, only 5% of the time or 1% of the time. But at a user waiting 10 seconds, there are people leaving your website. You're leaving money on the table. And so it becomes a big problem of how do I deal with this tail latency, right? And this tail latency performance, this variance, is almost as important as the average case time. And so companies, really spend a lot of time on this. I really like this Tail at Scale by Jeff Dean, from Google, sort of kick this idea in the mainstream, really like, hey, we have these processes and these tail latencies cost us real money and we really care about them. Now, I didn't like it because it was kind of from a Google perspective about network latency, load balancing, and so it made it seem like a real systems issue. And my question is, no, it's not just a systems problem, right? Like this is not just something that people are going to talk about at SPLASH or whatever. Like this is a software problem. And what do I mean by this? Well, this was a great story I heard from some Node.js people. I'm running a big service, and I'm serving requests, and it's all great. And yes, the triggering cause is there was a network glitch, right? But what then happened and really caused our problems was this network glitch caused us to have some requests pile up. Since these requests usually were short-lived and they got collected in the Gen 0 garbage collection, but now they were long-lived because they were piling up, so they got promoted. That meant we had a long pause for a Gen 1 collection, which caused more things to pile up and more things. So our service just tailed off and died here. And that was the real, the trigger was this network issue. But what killed us was the software, right? And this is one that's network involved, but there's some pure software ones too, like there's some regexes. The regex of doom was a popular denial of service attack for a while. A simple looking regex this long has an exponential time. People would attack hash tables by causing malicious collisions. And of course, GC, everybody's familiar with janky UI with GCs. So I was like, hey, this is really a software problem as well. It's not just a system problem. And interestingly, like I said, I started thinking about this from a software quality reliability issue. But these problems, like it doesn't matter if my application crashes because I had a null pointer exception, or my application is unreachable because it has terrible tail latency and it has a denial of service attack. Either way, my people can't use it, it's not doing its job, it's unreliable software, right? And so the question is, how do you design a language that solves some of these problems? Like, can we think about this in a bit of a holistic way? Can we eliminate certain features that cause these problems? So let me talk about the kind of the project I've been working on is this Bosky development stack. And the goal here is to, from the ground up, build a programming language and a runtime that's designed to build high reliability, high assurance software. And I kind of take the opposite approach of, hey, I'm going to add a cool new language feature or build a super new clever analysis, because I met a lot of people probably smarter than me that tried those things and they improved the state of the art. But if you look at where the state of the art is today from where you want it to be, it's a huge gap. So I was kind of like, I don't know if I can push that stone up that mountain. So I'm going to take the opposite approach. I'm going to get rid of things that cause me problems when doing program analysis, and interestingly, that cause problems when doing like performance optimization. So one of them is the language is immutable. So there are no reference, you can't mutate values, everything's referentially transparent. You cannot view aliases or mutation or anything in the code. It's semantically invisible. There are no cycles in data structures. Like, seems a little funny, but it turns out to be really useful. One I really like is there are no loops, no iterative loops, and we try and discourage recursion, so we don't want inductive invariance and all that gross stuff. The semantics are designed to be fully deterministic, so that is, of course, no undefined behavior, that's right out, but not even things that are implementation defined or maybe version defined, like what's the enumeration order of keys in a dictionary, right? And this is kind of funny to me, but it's interesting. Over the years, JavaScript specs have gotten more and more prescriptive about the way things are done. If you look back, early JavaScript, it was enumerate keys in any order, it's great, we don't care. And as they've added new features, it's you must enumerate keys in the order that they were inserted in, because developers got really tired about guessing between which version of browser and which, different companies' browsers did it in different orders and having all sorts of weird bugs. But so this is another one. And lastly, well, PCRE regular expressions are really weird, so we're going to do a really, regular expression language. And so how does this stack up? So with these features, now can we think about making different choices about how we design a runtime? Oh, and let me show one other thing. Quick question might be is like, wow, that's a really constrictive language, right? Is any developer in their right mind going to get near writing this? And I don't want to go into detail, but in some, no, we're able to connect this nice IR to a fairly friendly surface level semantics for developers. This is Bosky code. Modulo a few keywords, it's actually valid TypeScript code. You have nice block structures, variables that you can reassign, returns, all sorts of good stuff. So if you're a TypeScript developer, you can kind of look at this and be productive, like shockingly quickly. And that was a very nice thing we were able to kind of beat out of it. But anyway, so hopefully that sets up the problem interestingly. We make a couple of design decisions here, which I think are kind of nice. The first one is obvious. Well, we want everything to be deterministic, and there are a lot of things in like a standard library that are not, right? So usually if you look at your standard map or set, it's built with a hash table. And hash tables are really cool because they give you constant insert and lookup time, and they're all great, and they have a slow case where you have to rehash at O of n time. But if you look at these things, if you look at like V8 code, there are all sorts of fun bugs about people like using adversarial values to plop in and cause it to continually rehash, right? And of course that's bad and you can work around this. But no matter what you do, there's going to be some unlucky user that just happens to have the right workload that causes you to do a bunch of rehashing, right? So you get this long tail of variability. And this kind of goes back to this tail at scale paper. even if you have a very small percentage probability of hitting a slow thing, if you have 10, 15, 20 things that have a slow path, eventually you're going to start hitting a lot of those once you're at scale, right? So the cool thing is we can actually get rid of these. There are actually well-known, nice persistent data structures like RBB vectors or using TIM-sort that give you not just great guarantees on the worst case bound, so you get this omega bound on your worst case, but they're actually n log n, or you can make them effectively constant. So they're not actually that much slower than what was your cool optimized data structure. Plus, they have much better variability. We can also get rid of PCREs to get rid of a bunch of these regex problems. And this is great stuff. You don't even, I mean, kind of Bosky is nice to do this in, but you could do this anywhere. But where the kind of stuff real fun comes from is when you go in memory management design, right? So what we're going to do is we're going to take an old and kind of simple algorithm. It's a really fun way to think about doing memory management. So I'm going to do a generational collector, and I'm going to have a young space with a bump pointer. And for the old space, I'm just going to use reference counting. This was kind of introduced in 2003. So it's very simple. But if you go in and try and implement this for something like Java, you have a lot of problems, like even though the old space is reference counted, you can't collect cycles with a reference counter, so you need a backup cycle collector. So you're still going to eventually pay some stop the world for the whole heap pods. There are other things like, oh, you can mutate objects. So if you have your application doing a lot of mutation, you're going to have to keep track of these remembered sets, and you're going to have to update all of that. So the cost per collection is not actually just the young space, but it's some application-dependent size on the other thing, right? Well, the cool thing is all these features of Bosky, like, get rid of that. So just by the design, we don't have to have multiples of the heap sort of spare space to make the collector efficient. We just need the space of the memory, which is the young space, and then the old space is ref counted. So we have a constant overhead garbage memory use, right? Since we can't mutate anything, we have a fixed amount of work, so we actually have kind of a real-time collector guarantee here. We're just going to sweep the young heap. We don't need to run a cycle collector. We don't need to do remembered sets. We don't need to do anything, right? So we have a guaranteed real-time garbage collector. The pauses are guaranteed, right? So, and then finally, it's application code independent. Since we don't need to do write barriers, we don't need to do remembered sets, we don't need to keep precise refs on the root, precise root set of anything. So now we can aggressively optimize the runtime as well. So this is really cool. We can do all these neat things, and we don't have to have any sort of complex, clever, crazy machinery. So this is a work in progress, right? Obviously. But this was interesting for me because the focus of the work was, this project was reliability. Like, I want to build high reliability software. But, as I said, runtime predictability and consistency are actually part of that reliability. It's actually a holistic thing, right? And a lot of the things that we did to simplify being able to do proofs with an SMT solver actually allowed us to simplify runtime design and be much more aggressive in our optimization. So it's very interesting to see these two things playing together, although oftentimes performance is seen as a complexity thing, but it's really performance is just making your life simple and then doing the obvious thing works shockingly well. So this is, a work in progress. So obviously I proposed some algorithms here. They have very nice theoretical properties, but hopefully I'll be back here next year giving you some black and white benchmarks on these. This was cool, but it also kind of showed that, hey, these properties in this runtime actually open up some other interesting avenues as well, right? So if I know where, if I know that there are no writes to any objects, can I start doing some compiler optimizations much more aggressively than if I had to worry about maintaining a bunch of read-write dependencies, right? Can I do a much more aggressive common sub-expression elimination kind of pass, right? Very interesting things about, like, my code is now fully deterministic. Does that make it a lot easier to think about how doing recovery or migration in a distributed system works? So I thought this was a really exciting demonstration of how these properties enable more than just verification. They enable you to do interesting stuff up and down the runtime stack. And so with that, I think I got a couple references. Like, we are working in GitHub. You can take a look at everything there. Got a little blog going, and if people are interested in this regular expression, we have that as a separate repository as well, actually written in C, so that if other people wanted to try plugging it into some other application. That's a possibility as well. Okay, so I think I wrapped up. I see I have 1 minute to spare, so I have a question or two.
Hi. Interesting idea. I was thinking about if your pause times are proportional to the live set for young generation, how will you ensure that BOSC will scale with applications that require a large heap or have a high allocation rate?
Well, the nice thing is the pause times are basically proportional to the young generation plus the number of old objects that you need to die per generation. But you can batch those into them incrementally. So you can basically guarantee that the application will never outrun the garbage collector, and that the pause time is going to be bounded by the young generation. Now, if you make this like 16 megs or 32 megs, this might start to get a little longer, but this is, of course, maybe a throughput versus latency choice you could make. This is something I hope to explore a little bit more once we have a larger set of code bases to run and do some legit benchmarking. Like right now, the amount of BOSC code out there is not enough to make a really convincing experimental evaluation, right?
Cool, thanks.
Any other questions?
Have there been many situations where the rejection of implementation-defined behavior at the language level has led to kind of needing to use algorithms with worse time or space complexity?
Well, let me put it this way. The asymptotic one is always a bit funny, but I think the RBB vector is an interesting one. So this was, it's basically using a tree for implementing something that looks like a vector in C++, right? So you can do arbitrary insertion and deletion. Now, the interesting thing is the way they do that tree, they argue that it's like you can get like a 4 or 8 gigabyte long list with a max depth of something like 7 or something. So they'll say it's effectively constant. Now, that's true in an asymptotic sense, but obviously you're going to do additional pointer dereferences. So you're going to, from a practical standpoint, the cost is going to go up. Now, this is a place where, if you look in that paper, they benchmark, I was using vector and I was using this RBB and I wrote Java code that sort of did a map the way you would in Java, like it iterated index-wise over. Now, the rough part is that means that for every index, it's constant in the C one and it's kind of 7 dereferences constant in the RRB one, which makes it, a 7x slowdown is kind of painful. But the interesting thing is, if you look at the way BOSC works, there are no loops. So this kind of point-wise operation is not possible. What you have to do is use higher order functions. So there's like a map or a filter or a min or a max. And the nice thing there is if you're mapping over this vector, the result vector is going to be the same size as the original vector. So rather than do a point-wise insertion plus the rotations and all that stuff, you can just allocate that memory before running and then just zip over. So that performance delta actually shrinks. So yes, there are places where it is in theory or it is in practice more expensive, but actually the simplicity and ability to understand what the language is going to do allows you to, I think, optimize a lot of that away. Again, this is an area where that's my back of the envelope calculation, but it'll be interesting to see exactly what that delta is when the benchmarks hit the road.
Cool, thanks.
Yeah.
Pichler.
Pichler, right, okay.
I mean, the German pronouncing is
Yes.
Pichler, but it's hard to pronounce, I guess.
I'll try.
But Pichler is fine. So. But thanks for asking.
Right, everyone, I think we'll make a start now. There's not enough people in the room, but you are the diehards, and you're here, so well done. Last session of first day one here, and last session of VMIL. So we've got 3 talks. Can I just make a quick request, please? For those who are doing the talk, please leave about 5 minutes or so towards the end so that we can actually ask some interesting questions. And with that, we have our first talk, which is on automating hybrid execution of ahead-of-time and just-in-time compiled code. It's been done by Christoph Pichler, right? And take it away.
Thanks for the introduction. This work is also, so I'm doing this work with a fantastic supervising team, so also thanks to them. And I'm from Johannes Kepler University in Linz in Austria, and this work is also done in cooperation with Oracle Labs. So one of the first questions when attending this talk is, why should we care about hybrid execution, and which kinds of executions are here merged? So imagine you have your source code. A typical way is to compile it to machine code. This is done ahead of time, so it's compile time, and then at runtime we run this code. So this is commonly known as ahead of time compilation, where you see that the optimization is done at compile time, and then the code is run at runtime. However, there is also a second way of executing programs, which is to use an interpreter. And when we analyze the code into an interpreter and profile it, we can also optimize it and produce machine code just in time. Therefore, this is called just-in-time compilation. And here, execution or interpretation and optimization influence each other. And we want to combine these 2 approaches for the same source code, because for ahead-of-time compilation, you have the nice property that there is no warm-up costs, but for JIT compilation, you can achieve a very high peak performance. And this is the reason we want to combine it to get the best of both. And we implemented our approach on GraalVM and for C code as an example. And how this is done is, there is GraalVM offers the LLVM runtime Zulong, and if you use Clang, for example, or Clang, then ahead of time, this compiler generates LLVM-AR and then also emits binary machine code, and this can be shipped in one file. And if Zulong receives such a file, it then creates an abstract syntax tree out of the LLVM-AR, and this abstract syntax tree is then forwarded to the JIT compiler. However, there is also the opportunity to use the native function interface of GraalVM, which offers to directly execute the binary machine code on the native side, on the CPU. And this is our hybrid execution model. So we have native execution, where compilation happens ahead of time, and we have managed execution as well. And those who attended VMIL last year might remember a similar slide, because there we presented the basic approach where the decision how to execute the functions are taken by the developer. So the developer had to annotate the functions more or less. This was more a proof of concept that hybrid execution is useful. And now we want to get a step further. But first, some technical basis. So we have source code, and in this example, we have 3 functions that are calling each other. And the abstract syntax tree looks, if it's a bit simplified, it looks like this. Then machine code looks like this. And let's say now we want to run B in the native mode and C in the managed mode. The way how we had to change execution is to forward the calls to B, for example, to the native side. And if we want to execute C on the managed side, we also have to forward the call from the native side to the managed AST node. And the modifications on the native side were not there last year. So this is an extension we had to do for the automated approach, and they're also platform dependent. But our goal now is to extend this and to do an automated decision. On the one hand, the programmer doesn't know the whole program code, and also doesn't have to have the deepest compiler knowledge, so to say, if this decision is automated. And for this, we start the execution by managed execution only in a profiling run. There we can track the program and create a call graph with necessary information. And then we apply some calculations. We write everything into a specification file, which is stored. And if there is a follow-up run, we can then use this information, and then the functions are run natively if our heuristics decided to do so. And talking about the applying heuristics already, this is the major part of the presentation now, because this was also the major work. It was not that we directly came up with this, but it was an iterative process and still ongoing process. So the journey has not ended yet, but this is the current state. So the general problem is that we have a function f, and we have to decide, do we want to execute this on the managed side, or should we go for native execution? And the current way is shown here, actually a little bit past, because the paper deadline is also already some months ago. And I will just explain those 3 steps in detail now. So the first question is if the function accesses managed data. And this is important because GraalVM is a polyglot execution machine. So when we execute C code there, and also source code of other functions, it can be that the C code accesses code of other functions. For example, today we had a lot of Python talks already, and also C extensions, native extensions we already mentioned. This is a classical example that you have some Python code and some C code, and of course those 2 languages, or code of those 2 languages, will interfere with each other. And let's start with a simple function addPoint that adds a point to a global data structure. And if we assume that everything is on the managed side, we have a function addPoint and also a point list, so to say, called data m, or data managed here. Then the function accesses the data structure. This can also happen on the native side, and this is also possible if we have a managed function, that the managed function accesses the native data. However, in the other direction, we have a problem. The details are listed in the paper. The simplified major reason is that we have to guarantee the semantic correctness. And we cannot, for example, store a JavaScript object correctly in C, but we have to use the JavaScript runtime for this. And therefore, this has to be managed. But it can be, so we have 2 different cases. In the easy case, for example, when it is a managed C struct, it can be easily converted to the native side, because also the C code can be compiled to the native side. Then it's no problem to access the data from both versions. However, in another scenario, which I will show on the next slide, it can be that the managed data cannot be converted to native representation. And then we have to execute the method that exits this data also on the managed side. So as an example, we could have C code here. As shown, we have the addPoint function. And if the data points to an array, then it could be that the first 2 points, for example, are C points. If this is on the managed side, it can be moved to the native side without problems. But if we have a Python point, for example, then we have to access this addPoint method on the managed side. Important to mention here, if we only access the elements 0 and 1 of this array, the function can still be executed on the native side. So it's really when we access the data element itself. So this is the reason, if we access managed data, then we have to go for managed execution. The second point in our heuristics is to take a look at the static function size. And because we want to achieve a fast decision, of course we could analyze the whole call tree here and would get an optimal result, but we don't consider this as possible because we have to get fast to a relatively good decision. And for this, we took a look at the function size, and it's not 100% correct what is shown here with the small text. Therefore, we will take a look in detail. So we wrote several C functions with different sizes without control flow. So this is important that I mentioned this here, and tracked the performance. And it was nice to see that we have linear dependency here. And from this point of view, it's clear if a function is larger than 30 kilobytes of LLVM bit code, then we execute this on the native side, otherwise on the managed side. However, the no control flow is a bit tricky, because you can relatively simply come up with an example where static code size and the amount of executed instructions contradict each other. So here, for example, we have a simple loop with 1,000 iterations. And there you can see that the second example, which has the larger static code size, has less executed instructions in total. And as said, we don't have to go for a perfect solution here because it's just heuristics, but we here just assume that every loop level increases the function size by 10. So we go for the maximum level of nested loops and multiply, we actually, for every nested loop from the maximum size, maximum level of nested loop, we multiply this by 10. We also try different numbers, of course. It's not that we just pick 10, but 10 lead to the best result. And the number of static loops can be also relatively fast determined. So in this example, we have the code on the left side, which contains 3 loops actually, and 1 branch, but now we only care about the maximum loop level. And LLVM is structured in as a control flow graph, so we have basic blocks, and we just count back edges. So for the while loop, the graph looks as follows. For the outer one, then we have a while loop in between, which is just 1 basic block, and then we have another different basic blocks, which also describe the green while function here in the middle. And what we do here is we just enter the basic blocks with an back edge, so either it's in or outgoing. We put them in a sorted list, and then if it's an ingoing edge, we know that the loop level will increase. If it's an outgoing edge, we know that the loop level will decrease. So we just iterate at the end over this table, and then can determine the maximum number of loops. So this was the second criteria. And then we have still some functions. So only the large functions are set for native execution, and the smaller functions are still not determined. And for these functions, we take a look at the call overhead. So when a native function calls a native function, or a managed function calls a managed function, the 2 top cases here, you see that there is roughly no call overhead. However, when we change the execution mode, of course, also there are settings in the runtime that have to be set, for example, and especially when you do a so-called upcall, so when there is a native function calling a managed function, we have a very high overhead here, which cannot be neglected. So imagine you have a lot of small functions. For example, our most call functions are actually in the benchmark then the increment reference and decrement reference methods of Python, for example, in C. Imagine you do a chain of small function calls. If they always switch back and forth between the modes, you have a lot of call overhead. And therefore, we use the call graph information which we have. So starting from a function f, we have a managed and a native caller, and also the call frequencies. We also have the call frequencies of the callees, so the function that f is calling, and then we just assume both sides. So first, we assume managed execution. There we know that we can ignore the managed caller and the managed callee. But for the native caller, we know that we have up call costs. For the native callees, we know that we have down call costs. And then we just put this together in a simple formula. This looks a little bit more complicated, but it's not very complicated at all. It's just calculating the time. And here there are 2 variables, in u and out u, which I have not explained yet. So this is the number of undetermined functions yet, because we still have functions where we don't know how we want to execute them. And for them, we just assume that half of them will be managed and half of them will be native. And this is where these terms come from. And then we do the same for native execution. So we know that we have down calls from managed callers, and if a native function is calling managed callee, this is an up call. And similar, we use the formula for this situation, and then we do a simple comparison. And with this, our simple heuristics or our fast heuristics is finished. So for an example, we use a Python application, for example, that has a C extension, and now we take a look at the C extension. So first, we check if the function accesses managed data. And this is the case because the function f in this case accesses the Python data var. Therefore, f has to go for managed execution. Then we can check the size of functions. And the function C is a large function here. Therefore, it's we mark C for native execution. And then we do the call overhead calculation. And I haven't drawn the call frequencies here, but we just assume that this is the result in this case. Since the time elapsed between paper submission and now, for example, what we also tried is if E is a very small function, we duplicate the function or we run it in both modes, but the results are preliminary and not really fixed yet, and we also would like to discover the results. But what we did is if E is called from B, then it's executed on the managed side. If E is called from C, then it's executed on the native side, if E is a very small function. This is also something we tried in the meantime, but this is not written in the paper yet, of course. Yeah, so with our final result, let's take a look at some benchmarks. Of course, we didn't try just the Python benchmark suite that is available because our work has been done for C and for native extensions. So we ran Python programs with native extensions. And we always tried them in 3 different modes. So the first mode to compare is fully managed execution. So every function is executed in the managed side. The other thing we tried is native execution for most functions. This means all functions that have to be managed run managed because they access managed data. But for every other function, we leave it for native execution. And then we have our hybrid mode with the proposed heuristics you saw on the last slide. And I picked up 2 benchmarks where to show interesting behavior, so to say. The first one is the LXML benchmark suite. So here, XML data is parsed and there is work performed on it. There are 20 different tasks. What we measured is the time it took for the data to be loaded. So this is the left column here. And then out of the different tasks, they can be grouped into annotation tasks and path tasks, or path finding tasks. So we group them by the general task, so to say, to see the interesting behavior. And what can be seen for warmup performance is that native execution is always performing best. This is no surprise. This is what we expected, because if more code is executed on the native side, of course, there's also less analysis by the profiler for JIT compilation necessary. And then we have, for peak performance, we have 2 different results. The one is for annotation tasks. We can even, with the hybrid mode, even outpass the other 2 versions. So here, the hybrid mode really pays off. On the other hand, there is also code where the hybrid mode performs less than fully managed execution. And this is, for example, because the GraalVM JIT compiler can then aggressively optimize. This is a very complex system, a very complex compiler. There's inlining involved, and if we move certain functions to the native side, of course, the GraalVM JIT compiler cannot inline these functions anymore. And this is just one example why fully managed execution is sometimes a better choice. And also in the follow-up work, we would like to improve our prediction skills, so to say. So if we get some piece of code, we would like to predict in a better way as we can do now which mode should be chosen. And the other benchmark I would like to show is the JSON benchmark. So when we go back, this is kind of the same situation we had for the annotation tasks for the middle column here. What is done there? JSON data is loaded and parsed and then dumped again. And what can be seen here? So on the one hand, for loading the data, the native mode is the better choice. However, for dumping the data, the managed mode is the better choice, which is the bar at the bottom. And our hybrid mode is always in between those two. However, if we take a look at the total time, our hybrid mode is faster than the accumulated times of both modes on the side, so to say. And this is an example where the hybrid mode finds a sweet spot. And this is also why, for example, the annotating task before can achieve a speed up, because we find a middle way of two different modes. However, as already said, we would like to also investigate a little bit more and being able to predict in a better way which execution should be taken. And what's also interesting is if we have, because currently the decision how a function is executed is taken at the beginning when the program is loaded. However, we would like to also do this at runtime, because, for example, we can start more on the native side, and then if we realize that maybe switching to managed execution is useful, we can switch to managed execution to enable high peak performance, but we still got a good warm-up performance due to the native execution in the beginning. So to wrap everything up, we proposed hybrid execution in the beginning with an automated approach this time, such that there is no work left for the programmer. We came up with a fast heuristics. I'm sure this is not the best heuristics you can come up with, but we needed an approach which evaluates fast. And then we also saw that it does not always perform in the best way, but there are situations where our hybrid mode is definitely a thing for a good choice. And with this, I would like to thank you for your attention and hand over to the discussion part. Thank you.
Hi, interesting topic. One thing that bothers me with in such a setup is the overhead that one has to pay to identify if the AOT code is valid or not. Because you have some AOT code which is already stored, and now the bytecode has changed, the class files have changed, right? So now all those checks will be added to this series of steps, isn't it?
The thing is that in our system, let's check it. Maybe there is even a faster choice for this. Yes. That when we restart the process, in this case, we still, even the just-in-time compilation starts from scratch again. So we really start with a correct program state again, because at program initialization, we say that that some functions are executed on the native side, and some functions are executed on the managed side. And then the program, of course, the GraalVM JIT compiler can now not look into the native code, and therefore it just assumes that the native code is correct itself, but it does not reuse.
No, I guess here's the deal, right? I mean, the JIT code has been, while the Java, the JVM is running, the JIT code is generated, all right? And in that, there is a call to an AOT method.
Yes, but profiling restarts from scratch again in the next run.
In the same run, so it's a long running program.
Yes.
In the long running program, there is a call to an AOT method.
Yes, but there we invalidate the things the JIT compiler did. So we restart from scratch when we use the decision.
Okay, yeah.
Of course, there is also, I think the last talk or one of the next talks is to reuse JIT compiled code. This is another approach. We really go for the ahead of time compiled code in this case.
Yeah, I might miss early part of the presentation, but let me clarify the motivation. So I think the target code, source code, is in the C language. Is that right?
Yes.
So I wonder, well, because the C language is pretty static, so I wonder why you have to, do AOT compilation for the C code.
So I'm not sure if I got the question. The question is why we also use JIT compilation for C code if it can be.
Yeah, okay. To me, because the source code is a C.
Yes.
So doing the AOT compilation would be quite straightforward, and in a certain sense, you can do AOT for every C source.
That's true. Yeah. Of course,
why you have to switch?
If you have C code only, then AOT compilation might and probably will be the better choice. But we also have in GraalVM the situation that you can mix programming languages. And especially when you mix programming languages, it can happen that you have to access, for example, Python code from C. And if this point is stored in a C array, but it is a Python point, if you use GraalVM and execute this code, then automatically the Python runtime is invoked when we access Python data. So if it's C code only, then of course AOT compilation would be the better choice. But since we also have different languages that interact with each other, it sometimes is necessary to go back to the managed side.
Thank you.
Thank you for your talk. If I got it correctly, when you want to determine whether a function should be executed in native mode, you look at the at whether the callee and the caller are native or managed. And would it make sense to go a bit further in the graph, in the call graph, and to look at the nodes that are the caller of the caller or the callee of the callee? Because if I got it correctly, there is some cost associated to context switch. So would it make sense?
Definitely. The thing is, I haven't tested it for speed because we need a fast decision. If we apply an NP-complete algorithm for this, it might take very long. And if we can run the application before, and it doesn't matter how long it runs before, because we do the profiling run, and then at a later point in time we want the fast execution, then this would be a very valid choice. However, I have to admit I haven't tried graph coloring algorithms for this situation yet, because we want we want this process to happen fast. But definitely a good point, especially when we have the time in a situation to try this, because then we could also go for an optimal solution, I think, instead of just guessing which way would be the fastest.
Thank you.
Right. Okay. So my concern here is that you use some magic numbers in your heuristic there. There's a 10 for the code bloat size based on loops, right?
Yes.
And there's a 2 based on the fact that you arbitrarily split them 50-50. How many programs / benchmarks did you use to actually come up with those numbers?
For 10, we used the benchmarks presented here, because with those we could also achieve speedups. And for the 2, we actually also checked for, it was not exactly half, it was a bit more on the managed side. So it would be not divided by 2 and multiplied by 0.5, it would be multiplied by 0.56 or so. Again, this is also because we just needed to get to a fast result. But that's true, we could also adjust this. If we see that in a benchmark, for example, in the LXML benchmark, we use, I think, only a third or even less, 22%. Yes, here in this case, only 22% of the functions are native. Then we could also adjust this divided by 2 to make it more appropriate to the actual situation in the application. But we don't know this beforehand.
Right. So, but you do need to adjust based on benchmark then.
Yes, so we just saw that for the given benchmarks, this works well. We also tried it with different parameters instead of dividing by 2 with multiplying by 0.6 and other numbers. The reason why we stayed with 0.2 is it got the best results for the benchmarks we tried here. But of course, in this case, if we only have 22%, then the division by 2 is not the right choice, obviously. But we don't know beforehand how much functions will be on the native side. And this is why we go with the not really precise version.
Next talk, the last but one, is performance bounce checking for 64-bit WebAssembly, and I'll try and pronounce this right. Lucas Dollerer.
That's perfect.
Right. Okay,
that's
there
all
you
right. All right, thank you very much for the introduction. Before I start the talk, I want to quickly ask, who of you is familiar with WebAssembly? All right, perfect. Still some people who are not raising their hands. That's perfect because I prepared you a very short introduction. Does this work? Perfect. So everybody knows JavaScript. The way to make the web interactive, we use it to execute foreign code in our web browsers on our device. Pretty interesting. That's why it's executed sandboxed. To get some better performance with it, normal JavaScript runtimes will chit compile JavaScript, but still, like executing a full video game in the browser will still be a problem performance-wise. So the idea was to reuse traditional high-performance languages like C, C++, and Rust, which are like easily optimizable, or we know how to optimize them. We have working compilers for them, which have been built for many years now, and use them for compilation for the web. So there was a subset of JavaScript, this is still valid JavaScript called asm.js, which didn't use all the features, and then browsers could be optimized for execution of this subset of JavaScript. There was still too much overhead with executing asm.js, for example, for validating that it is actually valid JavaScript. So the movement now is to have a separate runtime in browsers and a separate bytecode, which is not JavaScript, which can be further optimized, and also the runtimes can be specifically built for it. This bytecode is WebAssembly. So the big benefit of WebAssembly compared to JavaScript is that we can reuse existing architectures to optimize this code, and also this code is statically typed, so we have way more optimization potential. All right. Alexis and I have been looking at bounce checks in WebAssembly, so I want to quickly introduce where we would encounter such a bounce check. In general, WebAssembly is executed, as I said, in a sandbox execution mode, so we can't access any memory that we didn't allocate. This is where this bounce check comes into play. Here's an example. I show you a very basic WebAssembly function, which just accesses some random point in memory and then drops the result. So looking at the first line is a local.get. This would be used to get the first parameter of our WebAssembly function. Let's assume the value was 0x40, which we then put on the WebAssembly stack. As you can see, WebAssembly is stack-based. So now we have that on the stack, and we want to continue with the load. This load instruction is a 32-bit integer load, and we can also specify an offset and an alignment. The alignment can be ignored for now. The offset is very important because it is a separate 32-bit integer encoded into the load instruction, which is added to the immediate pulled from the stack. So in this case, we take the 0x40 and add the 2 as the offset to get our whole address that we want to access in the WebAssembly memory. The WebAssembly memory can be seen down here in the slides. a schematic of it at least. This is in 32-bit mode, which means WebAssembly memory and the normal WebAssembly is accessed with 32-bit addresses. As can be seen here, our maximum memory size is 4 GB. The runtime doesn't have to use all this memory though. So in this example, we only allocated 256 KB, which is available to the WebAssembly code. This can be increased dynamically through instructions, or also can be specified as a minimum at the program start. All right. When we develop our runtime now, our job is to figure out where will this load hit our memory. Like, will it be 1 or 2, which are completely valid memory accesses and we can just load from memory, or will it be 3, which hits unallocated memory, which is not accessible by WebAssembly. So this should raise a WebAssembly trap. It is actually guaranteed to raise a WebAssembly trap, which basically means we abort the execution of the current WebAssembly thread. So this has to be determined by the runtime. And we'll look for how we can do this and how we can optimize this. And the rest is just easy. We assume this was 1 or 2, a valid memory access. So we get whatever we loaded from memory onto the stack, and we can drop it again. That's basically how WebAssembly works, how we could execute it. But we want to look more on these bounce checks and how we figure out whether this memory access was actually valid. So what one could come up with, a pretty easy solution is just, well, we know the size of the memory, we know the address where we want to load from, why not just compare them? And if my address is larger than my memory size, I can just jump to some code that performs a WebAssembly trap. Easy solution has 2 big problems. We introduce a branch, which is here the conditional jump. We hope that our branch predictor predicts this jump is not taken, but these are branch predictors. We have to trust that. And also one problem that is not too clear from here is in line 2, we're loading the memory size. Let's imagine this is a multi-threaded execution of WebAssembly, which is possible through the threaded threads proposal. Then this memory size could just have been changed by some other thread. So this is actually a cache miss, which could increase execution times a lot if we constantly resize the memory. So this load is also a problem. Even though this is such a problem, it is used by some runtimes for every memory access. Anyways, even the original WebAssembly paper already introduced an optimization of this. Normally, we will execute WebAssembly on 64-bit host systems, which means we have a 64-bit memory, or 48-bit, for example, virtual addresses for Intel CPUs. So we can actually just allocate our whole 32-bit address space of WebAssembly, which is 4 GB. Just not really, because as I mentioned before, we also add a 32-bit offset to the 32-bit address that we pull from the stack. So the entire address is actually 33-bit long. So if we were to allocate the whole addressable memory, we actually have to allocate 8 GB of memory. On our 64-bit host system, no problem. We can do this. And then we just say, okay, every page that is not accessible via WebAssembly, we just protect this. So on a Linux, for example, we do an mprotect with prot none. So every access to that memory will just fail and raise an exception. Pretty straightforward, as you can see. Our assembly, this is Intel assembly, by the way, sorry, for x86 CPUs. We can see our assembly reduces to just the memory access, which is nice. Memory pointer stays the same, so this can just be kept in some register, even we don't have to load this from memory every time, which is very fast. No overhead for bounce checking because everything is done by the MMU. This is very popular, and pretty easy to implement, so this is also used by most runtimes for 32-bit addresses. There's one last problem though, like how do we get from the invalid memory access, which raises an exception in the CPU, to the WebAssembly trap? We have to do this, like this is more an engineering effort. The paper I'm presenting was written for a database system that my chair develops, which is called Umbra. This is just a basic context to know we're writing our WebAssembly runtime in C++. And in the end, we generate LLVM code that is then compiled there. And this is not too important for the bounds checking, but just to get the bigger context, why actually going from a CPU exception to a trap can be kind of cumbersome. Because we have to go through the Linux kernel, which will generate either a segfault or a SIG-bus signal, depending on where we hit the memory, which will actually then call a signal handler for us, which we have to register. From the signal handler, we can't just long jump to some trap handler because we might have some resources open, so we need to call some C++ destructors. That's why we need to raise a C++ exception from the signal handler. This is not as easy as it sounds, because normally a signal handler is not a normal stack frame. You can't just unwind through this. But LLVM and GCC generate code to do this. So we can actually do this safely and then unwind through our stack to find somewhere the end of our runtime and finally count this as a WebAssembly trap. So there are some engineering efforts also behind this, but basically we trust the MMU to raise some CPU exception and then raise a WebAssembly trap from that. All right. So much for the background. Now the big problem. We're moving to 64-bit WebAssembly addresses. This is still a proposal, but it's important because some WebAssembly code might need more than 4 GB of addressable memory. And imagine game engines, for example, running in the browser might just need more memory. So just allocating all the accessible memory is kind of a problem, because that's more than our host system can actually provide. So our 32-bit guard page approach, which I just showed you, doesn't work any longer. So we need new bounds checking methods, and that's what we explored. So we present two bounds checking methods today: the 64-bit guard pages and the 2-level guard pages, which are basically two improvements of the 32-bit guard pages for 64-bit WebAssembly. One problem that I already mentioned, 32-bit WebAssembly actually ends up with 33-bit addresses. The same is true for 64-bit WebAssembly, which ends up with 65-bit addresses, which are a way bigger problem than 33-bit addresses because they don't fit in our CPU registers. They can't be used as address operands. And every arithmetic operation where we try to combine the immediate and the address just results in an overflow. So until the end of this presentation, we will just assume that addresses are wrapping in WebAssembly. The current proposal does not do this, but I will present options how to mitigate this issue. All right. So the first approach that we discovered with 64-bit guard pages, the basic idea is you will never need your whole 64-bit WebAssembly address space. So we just statically reduce it down to a smaller address space, which we do by applying a mask to your address and just checking whether the upper X bits are set or unset. Here, for example, you can see it. We just artificially shrink down the 64-bit address space down to 4 GB of addressable memory again, so like with 32-bit addresses. By comparing your upper 32 bits with a mask, and if one of these bits are set, we can then again do a jump to some trap, code that executes a trap. And if not, we can just go on. Like, no, you might say, well, this looks exactly like the software bounds check I proposed at the beginning. We just don't do a compare, we now do a test with a mask. Well, for this, we don't need the memory size because, oh, sorry, this is one thing I forgot to mention. Of course, the subsequent memory access we can then do with our normal 32-bit guard pages. So we just look whether we would overshoot our guard pages, then we jump to the trap code, and if not, we can just reuse what I showed for 32-bit WebAssembly. So this eliminates the need for loading the memory size, which should be good in multi-threaded environments, but we'll see in the benchmark how this turns out. The most promising approach we are presenting are 2-level guard pages. These also build on the idea of the 32-bit guard pages I presented for 32-bit WebAssembly, but enable us to actually cover our whole 64-bit address space with guard pages. All right. So here you can see the schematic. The WebAssembly memory and the microguard pages together can be seen as one unit, as we've seen then before for the 32-bit guard pages. But now we can't just increase our microguard region to the size of our memory, because then again, our memory, our virtual memory on the host machine is just too small for that. So we basically compress chunks of memory down and map them to one macroguard page in the macroguard region. Here you can see, for example, we always take a 2 gigabyte chunk of memory and map it to one microguard page in the microguard region. So addresses 0 to the address that hits 2 gigabyte minus 1 maps to microguard page 0, and all subsequent addresses to microguard page 1, and so on. Oh, sorry, no, not 2 gigabyte, 1 gigabyte. I got this confused. So for the actual access in the assembly, we first get the address, then scale it down, do some more arithmetic with it. This is basically just to calculate the address of our macroguard page. Do an access to the macroguard page in line 6. We never look at the result, because we don't care about the result. We just care about, is the macroguard page protected or is it accessible? If it's accessible, perfect. We can continue with our further memory access, which is the actual load in line 8, which then just accesses the address. And in line 8, this performs again a bounce check against the microguard region, which serves the same purpose as we've seen for 32 bits. It just protects the rest of our block, in this case the 1 gigabyte block, which is not yet allocated by WebAssembly. So again, in this example, you have 1 gigabyte plus 1 page of WebAssembly allocated, and the rest is not available to WebAssembly. So every access to 1 gigabyte plus 1 page and further either hits the microguard pages, which is a seg fault, or hits behind this 2 gigabyte line, which would hit macroguard page 3, or 2, sorry, number 2, and also is a seg fault. So we can actually make sure that for any further 64-bit address, you will only not get a seg fault if you hit valid WebAssembly memory. All right. Some further numbers for this. We can also calculate the perfect ratio between macroguard region and microguard region size. Basically, you could already imagine the smaller my microguard region, the smaller my chunks. So in this case, it wouldn't be like 1 gigabyte, but it would be 512 kilobyte or something like that. Then I need way more macroguard pages. Each macroguard page requires 4 kilobyte of memory for x86. So that also requires more memory. We can see that the optimal size of both is if they're both the same size. And then we can just find the minimum size for both, which turns out to be 256 gigabytes for each, so 512 gigabyte for both the microguard region and the macroguard region together for Intel x86 CPUs, and a WebAssembly page size of 64 kilobytes. All right. Now the most important thing, does it actually work? Is it faster than software bounce checks? And therefore we performed some benchmarks. These are 4 benchmarks from the spec CPU benchmark suite. Why only 4? There are so many more. Well, these are the only 4 we were able to compile with the current WebAssembly toolchain without modifying the benchmark. Some other benchmarks are very low-hanging fruits, but you would have to modify either the compiler or the benchmark. We didn't want to do that. And also a self-written k-means benchmark, which was written specifically for our database runtime. All right, this is, disclaimer, this is only single-threaded. So what we can see here in, I'd say, dark green is software bounce checks. Perform almost similarly to our 64-bit guard pages. As said, this is single-threaded execution. We expect that 64-bit guard pages might have an advantage for multi-threaded execution, but for single-threaded, they're as bad as software bounce checks. As you can see, this is normalized to execution without any bounce checks, because a valid WebAssembly program only accesses valid memory. So you can also execute it without bounce checks, but of course then it's not sandboxed any longer. In dark blue, you can see the 32-bit guard page approach. As we expect from the assembly we've seen before, there are no instructions introduced for the bounce checks. We just use the MMU, no overhead at all. And in light blue, you can see our 2-level guard page approach, which performs very well, like, I don't know, you can see it somewhere around 11% or even a bit more overhead, which is really good compared to sometimes like 2.4 times execution without bounce checks when you use software bounce checks. Yeah, that's basically it. I've got some more slides which handle the 65-bit thing for truncation. Yeah, I go through this quickly. They are more thought of as a discussion topic, probably, because currently we wrap 65-bit addresses. Again, we have 65-bit addresses because we take a 64-bit integer from the stack and add the 64-bit immediate that is encoded into the instruction. We currently just wrap them or accept the integer overflow. This might yield to false positives, so you might not get a trap even though you were supposed to get a trap. This is not a security issue though. Like, you will just access wrong memory. But it's still your runtime's memory, not some out-of-bounds memory. This is not spec compliant. So this is a problem because you're guaranteed to have a trap. So option 2 is we actually are spec compliant and handle these 64-bit addresses. There we have multiple options. Like the offset that is added is statically added. So if it's 0, we can just go on. There will be no overflow. Perfect. And then there are some possibilities how to check whether we will have an overflow. Every integer overflow is invalid, so as soon as we know that the offset and the address together are larger than 64, larger than anything that can fit into a 64-bit integer, we can just trap. So maybe our CPU offers some option to detect overflow when we combine these, and we can then trap. That would be perfect. Or we also did wrote down some idea here. There are many other ways how to check this. I'm not going to go into details here. Yeah. I think that's enough for that. There are possibilities to check whether you would have an overflow for combining these. All right, and that's already everything I had to talk about. I presented you the 2 approaches for 64-bit bounce checks for WebAssembly and our benchmarks. Thank you very much for listening. Yes, any questions?
Yeah, I kind of wanted to ask because when you're talking about when we allocate, for example, 4 gigabytes of the VM memory, how is that really, how are we allocating 8 gigabytes? I don't think we are. If you ask the operating system to allocate you null pages that are going to trap on the page fault, they don't get allocated actually. I think they just are non-existent. Like when you access that memory, virtual memory, it generates a page fault, and then the operating system just says, yeah, that's not a legal memory to access. I think there may be a problem when you have 64-bit memory, because there's a lot of pages, but I don't think you ever allocated much memory. I don't think where you have WebAssembly memory of 4 GB, you allocate actually 8.
So if I get your question correctly, so the first thing with allocated and unallocated, like everything where we say like we allocate these full 8 GB, but we only make, I don't know, less than 4 GB available to WebAssembly. What we actually do is, of course, the actual memory is allocated and somewhere in your RAM. The rest is just a shared copy of /dev/0, I think. Yeah, there's no page that is actually allocated. It's just an entry in your page table that will be used for these inaccessible pages until like you have the 8 GB full.
Do you need an entry in the page table though? Yeah, maybe. Sorry.
If you don't have it, your operating system could just place some other thing in there. Like if I then do a subsequent mmap call without providing an address, I could end up with another allocation in the space, which would then result in a false positive too.
Thank you. It was interesting. For the 65-bit, couldn't you do the 2-level thing, but just shift your both your offset and your base number before you do the comparison? So basically, do the same trick as you did with the 2-level one, except don't add the numbers, shift them both, and add the number, the shifted number, and then you could do the 2-level one just the way you did before.
I didn't think about this before. It sounds reasonable. I might have to think about it a bit more, but yeah, that could work. Yeah, because we only have to make sure that it doesn't overflow. So, and then of course we can also do the bounce check with the pre-shift. Yeah, that's a very good idea. I didn't think about this. Thank you very much for the suggestion.
Hi, I'm surprised at the results. So yes. So I was wondering why the 2-level guard page is much faster than the 64-bit guard pages. The 64 guard pages use the the 2-level guard pages accesses memory twice compared to the while 64-bit guard page access memory once, but it performs the branch instruction.
Yes. So for the 64-bit guard pages, you have the additional branch instruction. And if I jump back, you have to store this mask somewhere. So either this is a second memory access, or you have a register that you block for this. So we checked multiple ways to do this, a test with memory or using a register and stuff. This was actually the fastest one, so we stick with loading from memory, because that's then in your cache and it's pretty fast. But was your question why this is so much slower than the other one?
Yes.
So here it is important to notice that both memory accesses are completely independent. So your out-of-order execution can actually shift them however it wants to, and can also do the arithmetic calculation of your macro guard page address out of order. So we think at least this is a big opportunity for the CPU to optimize the execution of 2-level guard pages in particular, because you don't have that barrier of a branch between them.
Thank you. I understand.
Thank you very much.
One more question. Time for one more question.
I think it's also true that you can lift the first level check out of a loop, because you can, even if the loop wraps around, you're going to go out of bounds.
So if you were to access memory in a loop, or
Yeah.
Yeah, so this is also something we didn't cover at all in this paper. This just assumes that every bounds check is required. Of course, if you, for example, have a loop that goes through an array or something like that, you could also statically eliminate some of the bounds checks.
Even just the first level, you can just lift the first level.
Yeah, so if the loop stays in the same region that is covered by the same microguard page, yes, you can lift this outside of the loops. Yeah, that's also what we didn't look at. We just, in this research, we assume that every bounds check is completely new and required, yes.
Okay, let's start the speaker again. So, our very final talk for today. We have a speaker in the room. Yes, okay, there we go. I started to get a bit worried there. Go ahead. But while I introduce...
There's the adapter for
okay. Right, okay.
There you go.
Right, okay, so our very last topic for today and presentation is reducing feedback pollution, and it will be done by Sebastian Krinsky.
I'll throw it up on the screen in just a second.
I think. Right.
Yeah.
Screen mirroring.
Okay. Super. Right, I can start. Right, so hi, I'm Sebastian. The title of my talk is Reducing Feedback Pollution. I would like to start off with the overview of JIT compilation. So let's compile this simple sequence of code. The colors represents the types inferred by the compiler. The darker means less precise, as it's the combination of all other colors. And the add any instruction is the polymorphic add that handles multiple types. And at the bottom right, we see the type for the native add operation. Sometimes the compiler might be able to infer the type of some of the variables, be more precise, this integer in this case, for example. And then it will propagate this information and get more precise result types. So we can change the instruction to a more precise instruction. And if, on top of that, the type of the arguments match some native operation, we can also replace the generic operation at the native level with a more precise one. Now, this is not often the case. Sometimes we get the type of some of the variables, some not. So for example, in this case, we know the type for Y, we don't know the type for Z. And so what the compiler can do is try to guess the type. The assume instruction is the embodiment of this guess. And after that, the compiler can kind of resume the inference and restoring the precision for the next instruction. Now, if we fail, we de-optimize and resuming the unoptimized code. Now, we would like to improve this guess because the optimization is expensive. And one way to improve it is
we can insert record instructions in the unoptimized code. So, for example, in the animation here, we will see Z is actually yellow when we run it, and we will propagate this information into the feedback vector on the right. Now it's empty, and now it gets it's yellow. And then, now we have this information in the feedback vector. When we compile the function, we can use this information instead of just guessing. We can feed the compiler with this extra information and produce more efficient code. Or hopefully the guess will be better than just randomly guessing. If we run the interpreter code for a while longer, we already encounter yellow, but maybe we encounter green in this case. And we'll also propagate this information here, and we will merge it with the yellow, hopefully something like purple. And if we continue running it more and more, eventually we'll merge all the different behaviors in this one place, and the feedback vector gets polluted. Now, on the other hand, if we compile it too quickly, after seeing two fewer types, what can happen is that the guess will most likely be wrong. So if you are assuming, say, we're expecting a yellow, but then we see green, and then we will de-optimize, and something similar will happen. We will de-optimize, we will go back to interpreter land, and we will pollute the type feedback as well. I think we can spot a pattern here where we learn something, compile for it, and then we see something else we didn't expect it, we de-optimize, and we recompile for something more general. And this goes on and on until the type feedback vector is polluted and there's nothing more we can do. So after that, the optimizations we can get from a polluted type feedback are kind of useless. So how can we mitigate this problem? Well, we could do once in a while. We could just zap the information and say, we don't want this type feedback to become stale. And once in a while, we're going to clear it. That seems reasonable. The problem is that a program can have many phase changes, and we will keep tripping ourselves and de-optimizing and re-optimizing all the time. So let's see what other people did in the past. So this once in a while could be more complex than just once in a while. We could have complex heuristics, that's what they do in Jalapeno, for example. Among others, all the things that people do in V8, they delayed the collection of the feedback until the program stabilizes. And of course, we can always give up after too many de-optimizations. Another approach, rather orthogonal, is we can try to keep the information separated. And by separated, I mean we can store the information depending on the different context the program is running. And the context can be the type of the arguments, the call sites, even the call stack. And in this line, it's the truffle framework and the self-rewriting ASTs. Let's zoom in at the V8 for a second. If we inspect the state of a feedback vector of a function, and once in a while we clear the information, we will see something like this. We will encounter different colors. Looks nice. Now, if we don't zap the information, what we will get is something like this. Over time, after each invocation, after some time, the feedback gets more and more polluted. The kind of the idea of V8, they're working under the assumption that programs in JavaScript will have this unstable phase where they will see all these polymorphic types, and then after a while, the program stabilizes for fewer types. And then, having that in mind, if we delay the collection of the type feedback, we can just ignore all this, and then after this happened, we can start recording fresh, and we skipped all this polluted information. Of course, the programs need to fit into this pattern, which is not always the case, so it's not perfect. And just a few words for the self-optimizing AST interpreters. What they do is, in Truffle, is that instead of having feedback vectors, they store the information in the AST nodes, and these AST nodes get rewritten as they see different types, different information. So we start with empty feedback for this node, for example, and then later we see yellow, so we rewrite the nodes to now there's integer nodes, and then we see something else. Eventually, same thing happens, it gets polluted. So it's another approach, but the pollution is still there. Right, context. So before I get into our contributions, I want to explain context and contextual dispatch, and we will build on this later. This is prior work from our group from 2020. So as I said, one problem with speculation, if after multiple uses of the same function, we will end up de-optimizing, recompiling, the code becomes too general, and there's nothing we can do. It's stale and stays like that forever. And also, de-optimizing itself, it's costly, so we would like to avoid that. So one thing we could do is we could have multiple versions of the same function. We can compile, for example, for B0, the general case. It supports all the types, but we can also create a version for, say, for the yellows. And notice in this case, we don't have any assumes, and all the information, all the optimizations are inferred from the context. So that's all we need. Now, all right, so we don't have the assume, but we have to have something else. Before we jump into the code, we need to check that the arguments we have in our hands are compatible with the versions we are going to call. So we dispatch, for example, say for, we call f of a and b, we inspect the arguments, we see they are yellow, we have a version compiled for yellow, we'll call it. And the code snippet we have in the middle kind of summarizes this dispatching mechanism. We inspect the arguments, we call it calling context, we dispatch, which means we look up the right version, and then we call this version we found passing in the appropriate arguments. So let's see just a couple more examples. We have the calling context on the right. We can dispatch to this version that matches exactly. Then this version only matches the brown one. And this version matches the purple one. So what I want to convey here is that the calling context don't need to exactly match the compilation context. They need to be lighter or more precise. And so as long as that happens, we are free actually to pick any version that fits. But of course, we want to pick the one that fits the best, because this is the one that more likely provide more benefits. Okay, we could always dispatch to the red one, but then there's no gains to be had. Let's see how the feedback vectors interact with the contextual dispatch I introduced. Let's say we are running the function now we start with the yellow, and we pollute the type feedback. We are running an optimized code, so we are recording into this feedback vector. Now we run for the green, and again it gets polluted. It gets purple. Now, if we try to compile a version based on this feedback vector here, let's focus on the version v1. You can see that if we compile for the yellow context, we can still compile and good enough optimized version. Actually, it's the same what you had before. And the reason is that all the information we needed was inferred from the code for the compilation context. In this particular case, we didn't need the feedback vectors. So because we have more precise information, so we can freely ignore it. And this last example for the contextual dispatch, let's make it a bit more complex. Now we have a global variable G, and also we are calling into a built-in ID. ID is just the identity function. It's a very, very simple built-in. The only characteristic of this function is a built-in, and the compiler doesn't know much about it. And the only thing it's how it doesn't know the type. The only thing it can do is just to probe the result at the end and see what it returns. And these two are stored in the last two slots in the feedback vector. Now, if we run this kind of client script on the right, we're setting the global variable first, and then running f, and then changing the value of g, and then running f again on a different calling context. Eventually, the feedback vector gets polluted, and again, if we want to now from this feedback vector recover the information, we can see that, okay, for the first instruction, we are able to produce efficient code, but for the rest, there's nothing for us to do. So we need to compile for the add any instructions. Everything is very generic. And this gets us to our contribution. So it seems that the problem is that we are storing all the information in the same bucket, in the same place. So let's see if we can improve the situation by adding more of them. The idea is very, very simple. Instead of a single shared feedback vector, we'll have many of them, one per call context. Those call contexts were the ones that were on the left. And we will use this specific context to compile the version at hand and to drive the optimizations. So let's revisit the last example with this new lens. We call f with the yellow context. We create a new feedback vector for it. We fill it in. Then we call it with a different call context. We create another feedback vector, and so on and so forth. And notice that here the last two rows, or the last two slots in the feedback vectors, are not polluted anymore, because its information is kind of separated, compartmentalized. And if we now try to produce a version based on, for example, for the yellow context, we'll see that we can now recover the type of G and W, and we can speculate on them, which wasn't possible before. All right. On the implementation side, I told you the idea is very simple, but the implementation proved to be a bit more complex. But basically what we want to do is, or the main focus is, we want to make sure that we record the information in the right places, in the right buckets, and then that we use the information correctly when compiling. We implemented a prototype on a just-in-time compiler for R, which is something that we do in our group. And it's also implemented on top of the contextual dispatch idea I showed before. Now, the problem is, so where do we store this new information? We start with we have a function f. This is the internal representation of the function. On the one hand, we have all the compiled versions for the different compilation context and a single feedback vector. We turn into another table which has multiple feedback vectors per calling context. And notice that these tables can grow independently. So they don't have the context don't need to match, or the size don't need to match, but it's more likely that the calling context will be bigger than the compilation context. So we will call it for more places that we compile for. Now, how do we now store the additional feedback information before focusing on the where? The first thing we need to do is we need to have the so before it was easier because we always updated the same feedback vector because there was only just one. It's like a global thing we update. But now we need to have the call context available when we actually run a version, because there's no other way we can access to it. So we extended the dispatch mechanism that I showed before, and we also pass in the call context. And then we need to sort of patch all the places where we update the feedback information. One, for example, in unoptimized code, that means that all the recording points, whenever we see the type of a variable, a callee branches, now the interpreter machine will have this call context available, and we're good. Now in native, it's different. In native, the only places where we update feedback vectors are on the optimizations. Otherwise, we never touch the feedback vectors. And there's two cases. The simpler case is when we optimize from the same function that we called, and for that we extended the signature of the native code, and we also provide this extra argument for the calling context, and so that this information is available if we need to deopt. And kind of more complicated cases for when we deoptimize within inline code. And I want to get to that now. So the problem is as follows. So say we are compiling compiling the f function for the brown compilation context. And while doing that, we are also calling g with x, so it's the same type. At least, I mean, at this point we only have like a static type, which is what we are compiling for. But now we want to inline g, and we inline g using the brown call context, because this is all it's all we have now. Because we are not running the function, we're just compiling, and we need to compile the whole function. The only information we have is kind of static information, and this means that if we deopt from G, at least what we're doing for our implementation is we hard code the call context we are supposed to update if the optimization happens. And this is what we see here on the arrow. And let's look at this simple client code. Now let's say we call f with yellow, then we are calling also g with yellow, and say we optimize from g. Ideally, what we would like to do is to update the type feedback vector for yellow. That would be the right thing to do, the most precise one. And we didn't implement this solution, but basically what we would need to do is within the inline code, before the optimizing, we need to compute the current call context based on the arguments, and then the optimize for that. Of course, this is more costly because we are computing, we're synthesizing a context when the function is optimizing. Yeah. So basically, we turn from a static thing that is hard-coded to a dynamic thing, but it's more precise on the other hand. Now the other problem is using the information that we recorded. So let's say we are compiling F, and the compiler managed to pick up precise information for X and Y. And also now we want to inline G within F. But what happens if there is no feedback information available for the context yellow? In this case, we can pick a more general context. And in this case, we will pick the purple. So the question is if all the choices are safe, and actually they are safe because we can, everything we get from the feedback vectors is ultimately guarded in native code. So it's safe, but we want to pick the one that doesn't de-op too much and also brings some benefits. And lastly, for the merging information, sometimes we will compiling with a feedback vector which has some empty slots, some missing information. And for that, let's say there is some other feedback vector available for the same function with, let's say, complementary information. So we can do is we can merge this information into our feedback vector and compile for that. This is very abstract. In the paper we discuss different strategies, different heuristics for the merging. But yeah, but that's about it.
Probably have about quite time for one, maybe two questions. Anyone would like to?
So if I understand correctly, you are maintaining multiple versions for the functions, right?
Yeah.
So what is
I mean, that is prior work. We also maintain now is multiple feedback information for each of the versions.
Yeah, so what is the memory overhead if you use this approach?
So the contextual dispatch, what I showed initially, it's like this is our baseline. This is like the kind of the fundamentals of the compiler. For the the memory footprint, what we are our dispatch table that we use for storing the feedback vectors has up to I think 64 slots, because we can have lots of calling contexts, way more than compilation contexts. And also this is also the other problem, that the feedback vectors, we can have a lot of slots in each of the feedback vectors, because a function, it's recording everything it sees in the interpreter. So yeah, it can go out of hands. I don't have precise number, but it can go out of hands.
Thank you.
Yeah.
Here, question. So if you go back 2 slides, I'm not sure which slide. Keep going back 1, 2. So okay, that one, that one there.
Yeah.
The one after this. So in terms of merging new information into one another.
Yeah.
So there's contextual dispatch there. Plus you are also merging. So what's the overhead of actually merging these vectors together?
I mean, it can have some overhead. We didn't focus on the paper on the performance because we were more worried about the kind of what we wanted to do is measure the pollution we have on a corpus of R, and then see if there are any if there's any space for optimization. So first we wanted to focus on if there any space for reducing the pollution, and then we would focus on making it faster. The question you're asking is, okay, we are compiling, so we are not running native code, so we can spare some more time while doing that. Yeah, it's overhead, but it's overhead in compilation. It's not overhead running the native code.
Okay, let's speak again.
Thanks. So that concludes VMIL. So I just want to mention that next year it'll be in Singapore.